Okay, we'll start in a few minutes. Before we begin, I'd just like to mention what we want to get out of this study session. So we will work towards understanding curvature, assuming a background that is only multivariable calculus as well as linear algebra, and no more than that. So the text that we are following is Vector and Tensor Analysis by Harry Lass. Vector and tensor analysis. Yeah, just it's in the screen description as well. Okay, this is not a lecture. This is a study session slash seminar. Okay, this is a classic book, first published in 1950. It's in the same series. Hi. Um, no, don't worry. Like Christian, thank you so much for joining the stream. My goodness, like seriously, the idea is it's just, I mean, I said earlier that this is a study session slash seminar. If nobody joins the stream, it's going to be a study session. You know, um, I like it this way because I'm so grateful that people can point out my mistake along the way. That's so much more interesting for me. But yeah, like if you're busy, like just go ahead and do your thing. Okay, no pressure whatsoever. So, full background disclosure. I studied it. Actually, I self-studied it years ago, about 10 years ago, and I really never really touched this after that. Hi Buckingham. Thank you so much for joining the stream. I suppose you guys are from Europe or the UK, right? Because right now in North America, people are still working. So, thank you so much for joining the stream. So, what we're going to do is, as mentioned, move towards curvature. And the reason I'm doing this is because there's an upcoming stream on August the 8th on information geometry. So, in case you don't know, information geometry is the study of, from Alberta. I'm disabled, so I don't work. Oh, I'm so sorry. Bucking, I hope you feel better. Netherlands. From India. Wow, a lot of people. Thank you so much. Hope you feel better. I'm from Ontario. So it's it's perhaps, is it afternoon in Alberta? Actually, perhaps it's morning in Alberta. Okay. I never been to Alberta. I hope I can visit one day. All right. So yeah, I was saying I was preparing. I'm doing this to prepare for the upcoming stream on information geometry. And information geometry is the study of statistics, mathematical statistics, using the tools of differential geometry. So it's obvious that the prerequisites are pretty heavy. Okay, so yeah, Kashmir. I know Kashmir. It's like the disputed territory between India and Pakistan. That's all I know. What is vector analysis and tensor analysis about? Can you elaborate a bit? Because I never faced it. Okay, I'll talk about that. So my goal is to have a working knowledge of information geometry. And information geometry is the study of mathematical statistics and machine learning using the tools of differential geometry. So as you can probably tell, it is a very dense subject and it calls for a lot of prerequisites. And for that reason, we're going to study as study geometry on a need-to-know basis. Okay. When I was in university, I talked to a professor who does actual research in this field, and he was quite candid um, that he was quite candid that he is very it is very difficult to find graduate student in this area because of people who have strong backgrounds in mathematical statistics and geometry are quite rare. Um, I'll be honest, and I think it's not that much of a stretch to say the geometry in universities don't get enough exposure compared to, say, analysis and perhaps algebra. I don't know why, but it seems to be the case. But yeah, please feel free to correct me if I'm wrong. So, what is vector and tensor analysis? So, vector analysis is basically vector calculus, div, grad, curl, and all of that. Divergence, gradient, and curl. So those are the classical vector calculus you would probably encounter in a multivariable calculus class, and it's widely used in physics. For example, classical electrodynamics, fluid mechanics, that sort of things. Already, they can they can help you a long way when it comes to studying classical physics. However, vectors themselves aren't enough. Okay, even in classical physics, you don't need you don't necessarily. Sorry, I'm trying to say is even in classical physics, tensor analysis, vector analysis or vector calculus is not enough. Because if you move into fields such as continuum mechanics like the theory of elasticity and whatnot, vectors become inadequate. So you need an object called tensor. So vectors can be seen as one-dimensional array. Of course, that's a highly simplification. I mean, vectors have rigorous mathematical definitions, but you can think of them as an array of numbers. But then again, many quantities in nature cannot be described by a single array of numbers, and that's why we need tensors. Of course, down the road, we will describe tensor in various levels of sophistication. At the most basic level, you can think of tensors as multi-dimensional arrays, like a matrix, and its higher dimensional generalization. But of course, as our sophistication grows, the definition of tensors becomes more precise and elaborate. Okay, if tensor is merely a multi-dimensional array, that's just a data structure. Perhaps that's good enough for computer science purposes, but it still lacks physical and mathematical meaning. Hi, Vernon. Oh, hi, Kashmir is integral part of India. Okay, sorry about that. Okay, sorry if I offended the people of India that Kashmir is integral part of India. So a little bit about my education background. So I grew up in China as a child, and on our map, because of the special relation between China and Pakistan, I believe, they put the Kashmir as a disputed territory. Okay, so and yeah, that's just my impression in my mind. I guess a lot of people have the same perception about Taiwan. Like I know, like in Chinese maps, Taiwan is shown as Chinese territory, but internationally speaking, it's kind of disputed in various ways. But anyway, I don't want to get into politics. This is not the point of the channel. Sorry about that. Okay. Anyway, still, coming back to the subject of tensor analysis, in fact, differential geometry was initially developed using the language of tensor analysis. Einstein's theory of relativity was written in classical tensor analysis, and indeed, it is still to this day. Physicists and applied scientists like fluid mechanicians, such of those kind of field, still learn the subject from the point of view of tensor analysis. And which raises a question. Um, so yes, which raises a question that whether studying tensor analysis is enough for information geometry, right? Um, I think it is. It can still give us it can still give us very useful information, and for the most part, it should be enough. And why am I saying that? Because in a book by Amari, a pioneer in information geometry, called Information Geometry and Its Applications, the language used in the book, as far as I can tell, is overwhelmingly tensor calculus, okay, and not the abstract machinery of modern differential geometry. Of course, at a certain stage, you will have to formalize everything and be completely rigorous, but for the computational purposes, we can treat tensor analysis as our workhorse. Okay, so I don't think there's a conflict in that. Okay, it's like when we first study calculus, you rarely start with the axioms of real numbers, and then prove every theorem along the way, right? So it's very likely that when you first encounter calculus, you're shown a bunch of diagrams and heuristic derivation of every formula, and do a lot of practices, and eventually, once you're comfortable with working with calculus, and then you care about the foundation. When is your stream on video on? That's August 8th. If you click the stream tab on my channel, you'll see the upcoming stream. Yeah, so I try to, because earlier I'm just trying to make things organized by scheduling streams ahead, but I was told that it might feel spammy to certain viewers, and because certain planned streams are weeks ahead, right? So it's people can easily forget. Yeah, sorry about that. My idea is, like, I'm just so glad that people are joining the stream, because I initially planned, this is such a random stream. I just wanted to study the material to prepare for the upcoming information geometry stream. And I was like, okay, I have this community that people are very likely to be more knowledgeable than myself. So, and in the past, when I make mistake live, people point those out, and it saved me a lot of time. So I figured the advantage of doing a live stream, live study session, of just showcasing the raw process, is justified. Yes, I'm going to follow Amari's book. I'm going to follow. So first we'll start with a paper on the live stream, and then we're going to follow Amari's book. We're going to learn the information geometry, or we're going to learn differential geometry that is relevant to information geometry. So yeah, I almost purchased this last book, but ended up not buying it. I have too many books. Yeah, but I think a crucial flow research. In my opinion, this is the best vector and tensor analysis textbook. In my opinion, I didn't use it as an undergrad. It was recommended by a professor of mine on the same subject. But we used the course notes, the lecture notes by the professor. We didn't really use this book as a reference, and now I like to read into it. So it's sort of like my undergraduate class on real analysis. We used a different textbook, but the Baby Rudin textbook, the Principle of Mathematical Analysis, that was given as a reference, but I didn't have time to read it. It was given as a reference for the course, but we didn't follow Rudin. So it was later on that I decided to read Rudin seriously, and it benefited a lot. And this book is in the same series as Rudin, along with other famous books like the Complex Variable book by Al4. So it's such a nice book. The notation is outdated compared to more modern, but it's good. Yeah, I mean, it's still sufficient for tensor analysis purposes. I know, like Crucial is saying that I put the title called Classical Tensor Analysis. If modern, if you say, check out the modern differential geometry text, the notation is going to be a little bit different. But the thing is, I'm trying to follow Amari's text on information geometry, and he uses mostly classical tensor analysis, like physicists. So that's why I'm choosing this. This way, it minimizes the amount of translation for beginners. Okay, so enough background. Let's just get started. Okay, so stop talking about math and start doing math. All right. So first we will study summation notation. Of course, as with any early stage of study, there's a lot of notations and terminologies to familiarize before we can talk about serious results. Yeah. Tensor analysis. This is perhaps an old term. The modern term would be a multilinear algebra. So anyway, so let's start with the math. I will be reading the text because I cannot show the text on stream, and then I will add commentaries and verification, for example. It is said in the text, we shall be interested in sums of the type, which I'm writing right now. S equals A1 x1 plus A2 x2 plus all the way to AN xn. So we're interested in this expression. Okay, and now the book then says we can shorten the writing and write S equals the sum of AI xi, I goes from 1 to n. So this is simply the summation notation. Now it will be much more convenient to replace the subscripts of the quantities x1, x2 all the way to xn by superscripts. Okay, so we're going to replace the subscript I in xi by a superscript. So now the sum becomes AI xi. AI is a lower index, and xi, the I, is a upper index. So that's the new notation. Notice the superscript do not stand for powers, but are labels that allows us to distinguish various xi. So this is not power. Not power, okay? If you want power, you do a bracket and then say square. Not power. Okay. So now, and the next step is to get rid of the summation notation and simply write S equals AI xi. So it is probably clear from the context that how many terms are involved. Okay, typically in applications, n is the number of coordinates you need. And once you finish a setup, say, okay, our problem takes place in a three-dimensional space, then n is 3. And it should be clear from the context, so without writing n, there's not much information loss. Okay, so it's just a way of safe writing. Okay, mathematicians are human too. They get tired and become lazy, so they invent shorthand notations. So far, nothing mathematically interesting happened. It's just the same equation in different notations. Okay, so the repeated index I is summed from 1 to n, and this is the Einstein's notation due to Einstein. All right, let's move on. And it says, whenever a letter appears once as a subscript and once as a superscript. Okay, let me reread this. Whenever a letter appears once as a subscript and once as a superscript, we shall mean that a summation is to occur on this letter. Okay, so this is Einstein's summation convention. Whenever a letter appears once as a subscript and once as a superscript, personally, as a differential, I hate Einstein's notation. I don't like to use it. Yeah, it's a divisive topic. I think I can later on. In the comment, I'll pin a quote by a statistician who comment on the matter. It is a divisive topic. It is a divisive topic. It's people who argue people argue that index notation hides geometric intuition, and they're because which is fair, but at this stage we wish to develop computational machinery, because at some you will probably going to work with a lot of specific examples before looking at the general theory. Prefer explicit indices, not implicit Einstein notation. Okay, fair enough. So, so this means we shall mean that a summation is to occur on this letter. So this is the rule. If we're dealing with n dimensions, we shall sum from 1 to n. The index of summation is a dummy index, since the final result is independent of the letter used. So we can write S equals AI lower index, XI upper index, equals AJ lower index, XJ upper index, equals A alpha lower index, X alpha upper index, and equals A beta lower index, X beta upper index. So they all mean the same thing. Okay, so let's look at an example from calculus. So if you have a function f equals f of x1, x2, okay, all the way to xn, and from this point and on, okay, we're going to write coordinates of point with superscript. Okay, so yeah, Rigo asks, so by the statement AIXI is equivalent to, is AI, so Rigo is saying, so is AIXI equivalent to AIXI this way? Good question. We shall take a look at. I think as far as the sum is concerned, they are the same. But we reserve upper and lower indices for different types of tensors, okay, from what I recall. Okay, so because quantities with lower index and upper index satisfies different transformation laws. Okay, so for the moment, we're going to work with this symbol. I'm pretty sure this will appear later on. Okay. And of course, if you can, because AI and X are just scalars, right? So you can write it XI and AI. So it's just a change of letters. Okay. Because right now there's so little meaning attached to these symbols, we're not going to dwell on this. Okay. All right, so there we go. let's say we have a function of n variables. And we know from calculus, this is the chain rule. The chain rule for differential. So df, the total differential, is the partial derivative df over dx1 times dx1. I don't know how to even read this thing, huh? I just read it as d, but of course, in this formula, the pronunciation causes confusion. So hopefully, I apologize for it. You do read partial f. In LaTeX, you write partial f, right? Partial f over partial x2 times dx2 plus all the way to df over dxn, partial f over partial xn dxn. All right, yeah, so there you go. So now we have the summation. You can write it in the sigma form. Sigma I from 1 to n, partial f over partial xi, and then dxi, like so. And it is equivalent to the index notation, df over dx alpha, partial f over partial x alpha times dx alpha. Okay, so here, because partial x alpha in the notation is on the denominator, so we treat alpha here as the lower index. Okay, so that's the chain rule for differential, and the chain rule for derivative, df over dt. So you have an independent variable t, which all the variables in f depends on. x1 is a function of t, x2 is a function of t, all the way to xn is a function of t. That's like a curve in n space. Then df over dt would be still the same chain rule from calculus, it's just different form. Partial f over partial x alpha times dx alpha over dt. Once again, summation is assumed. Alpha appears once as the subscript and appears once as the superscript. Okay, so that's our first example. Example 1. Second example. And the second example is already relevant to the study of information geometry. As we shall see later, it is called a metric tensor. So we're interested in an expression of the form S equals G alpha beta X alpha X beta. So here we see there are two indices, alpha and beta. And they both appear once as a subscript and once as a superscript. So two summations are implied. Here in the text it says the index alpha occurs both as a subscript and a superscript. Hence, we first summon alpha, say from 1 to 3. So let's first summon alpha and see what that gives us. So you get G1 beta, X1 X beta, plus G2 beta, X2 X beta, plus G3 beta, X3 X beta. This is sum over alpha. Sum on alpha. All right? Yes, a matrix multiplication also is a nice example. And now you have this expression, and now you see every term now only contains beta as the only index. And because beta also appears once as a subscript and a superscript, for each term, a summation on beta is implied. So sum on beta, once again, from 1 to 3, S equals G1, you should have 9 terms in total, obviously. So you get G11, X1, X1. Okay. You see, we don't, I mean, you can, of course, write X1 squared as X1 quantity squared, but we prefer to keep the factors distinct. Okay. So now we have, so still expanding the first term in the expression above, second term here should be G12 X1 X2 and plus G13 X1 X3. Keep going. You have G21 X2 X1 plus G22 X2 X2 plus G32 X2 X3. There you go. Keep going. G31 is X3 X1 plus G32 X3 X2. And lastly, you have G33 X3 X3. There we go. So that's the full expression. And of course, we can use the double sigma notation. And it reads sum over beta from 1 to 3 of the sum over alpha from 1 to 3 and G alpha beta times X alpha X beta. So that's the second example. And we notice that G alpha beta can be treated as elements in a matrix. So you can organize this into a matrix, and the whole summation now can be reorganized into a matrix vector product. So this is called a quadratic form in linear algebra, in fact. x1, x2, x3, a row vector, times the 3 by 3 matrix G11, G12, G13. So in the whole process, we respect the index notation. Okay, not just the summation notation, but the index notation up. We keep upper and lower indices distinct. So here, throughout the whole derivation, G uses lower index and X uses upper index. Okay, and right now it's just pure notation. Later on, they will acquire a geometric meaning, because it has to do with how various quantities transform according to coordinate transformation. The overarching idea is when you describe something physical, geometrical, the idea is you want to keep the coordinates transform in a geometrical, meaningful way. Right? The geometric quantities should not depend on the choice of coordinate system. Coordinate system are scaffold for our own understanding. So this is this invariance that drives tensor analysis. Okay. And this is why tensor analysis is so important in relativity. Right? Relativity is all about changing coordinate system between different observers. Okay, so that's the matrix vector. Oops, sorry, old habit. I'm using the linear algebra notation. I'm treating everything using a subscript everywhere. That's not a good idea. So here, keep the subscript for x as should keep the index for x as superscript. Okay. For a beginner, I think it's easy to make that mistake because you're so accustomed to the calculus and linear algebra notation. Okay, so here we'll be very careful. Whenever just be consistent. Okay, whenever you use a superscript, stick to that. And subscript, stick to that. No, I'm not a professor. Hi, I'm not a professor. But anyway, I'd like to ask why Einstein is limited to counting 1 to 3. No, there is no limitation on, I guess the only limitation is finite summation. I don't think we use the Einstein's notation for infinite sum. There's no restriction on the upper limit for summation. It's just for this particular example. Okay, here, for example, in the it's usually typically actually I didn't write this down. It's written in the text. Some in 3D. Okay, so it's usually clear from the context what's the range for the indices. Here in the first example, obviously we have n variables. The summation must include n terms. Okay, so of course, every time you read a text or a paper, we first, and you see a summation notation, you first figure out, okay, what is the assumed range of the indices. Yeah. All right. So that's the summation notation. We're done with section. This is one section in the text. Okay, already done. And now let's move on to the next section called Kronecker deltas. Kronecker delta. Of course, Kronecker is a person. Quite interestingly, Kronecker historically had a lot of animosity with Georg Cantor, the inventor of set theory. So Kronecker was an algebraist and a number theorist, and he was what we call a finitist today. He had a famous quote called, God created the integers, and the rest are the works of man. Okay, so when Cantor proposed his theory of infinite sets, cardinality, countable, uncountable sets, and all of that, Kronecker fiercely reacted against it. Anyway, very interesting history of mathematics if you want to go check those out. But anyway, here the Kronecker delta is defined as follows. So it's a double index sequence. Definition. So delta ij, it's got an upper index and a lower index. Delta ij equals 0 if I does not equal j, and is equal 1 if I equals j. So as we can see, this is nothing but the entries of the identity element. Think of Kronecker as the guy who was wrong about Cantor. I don't think it's wrong. It's just different philosophy. It's different philosophy. If, it's a difference in philosophical position. It's like certain, even to this day, like certain mathematicians accept axiom of choice. Most of them actually accept axiom of choice, but there are people who reject it. Right? So it's like mathematics is actually, this might be a little bit controversial, but mathematics ultimately is not about right and wrong. It's about consistency. Of course, that's a philosophical statement on its own, but I'm trying to convey the idea of mathematics is about if such and such, then such and such and such. It's about what you are comfortable with assuming. Right. Lockheed said, the upper and lower indices of Kronecker delta is kind of flexible. I've seen move to both upper. Yes, they are. They are. For example, if you can, if we let the G alpha beta to be the Kronecker delta, what does that give us? That should give us just the Euclidean length, right? So later on we will call this G alpha beta the metric tensor. So if G alpha beta, here we both use lower index, and that's the Kronecker delta. If that's the Kronecker delta, then this S is just the Euclidean length in Cartesian coordinate system. There's nothing wrong with that. Okay, here we're just taking this as it says Kronecker deltas. Okay, so there are various versions of it. So this is our first Kronecker delta symbol. Okay, so here actually a little bit unclear in the text because due to the scanning quality. Here, notice some obvious result. Delta 1, 1 equals delta 2, 2 equals all the way to delta nn equals 1. Okay. Hold on. This gives us delta alpha alpha is n. Okay, so here's an identity because alpha, the summation index appears twice. So be careful here. Delta nn, n is a fixed number. It's not a subscript, right? That's not a script. That's not an index. Alpha is an index. Okay, so here delta alpha alpha means a summation of all of those quantities. I enjoy constructive mathematics, but finite mathematics always require finite choice. Without choice, you have nothing. Yeah. Yeah, so direct delta, yeah. Yes, direct delta, exactly. Direct delta in functional analysis or distribution theory is the version of Kronecker delta. Warren, I posted a video a few months ago on Green's function, in which I introduced the direct delta function as the continuous analog of Kronecker delta. Of course, that's the intuition. To describe direct delta rigorously, you need the distribution theory. Not probability distribution, but a separate discipline called distribution theory. Yes, what upsets you is uncountable choice, but choice itself is absolutely necessary. Exactly. It's the uncountable choice part that causes controversy. Anyway, so here. For that reason, whenever we use axiom of choice, we must cite it explicitly. Anyway, so here's the Kronecker delta. And let's move on. So what are other properties we can say about Kronecker delta? So if you have x1, x2, blah, 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 all the way to xn are independent variables, n independent variables, then the partial derivative dxi, partial xi over partial xj is the Kronecker delta symbol. Right? This is very easy to understand because x1 with respect to x1 has a partial derivative of just 1. With respect to every other variable, it's just 0 because they're independent. And the argument works exactly for the rest of the pairs. Okay, still, let's respect the symbol, respect the index position. I is upper, j is lower. All right. So thank you guys very much. So yeah, I hate. Thank you so much for the comment, but let's try to keep the discussion relevant to tensors. Okay, I hate to. I mean, perhaps it's my mistake to bring up the historical animosity between Cantor and Kronecker. I bring up these comments to keep the discussion more lively because the one recurring theme on the channel is that the mathematics we learn today are not handed from God. Okay, they are results of intellectual battles, literally sometimes. Okay. Does it only work for orthonormal? No. It has nothing to do with orthonormal. Because I never introduced inner product, right? It's just the fact that if x1 and x2 are independent variables, then dx1 over dx2 is 0. It's like in the expression for x1, there is no x2. It has nothing to do with orthogonality. Okay? This is purely from a variable dependency point of view. Right? dx1 taking derivative with itself is 1. This is completely trivial. Okay, nothing deep going on. There's no inner product, so no orthogonality. It's untrue for, well, let's say r theta, dr over dr is still 1, dr over d theta is still 0. How come d theta over dr is non-zero? Dr over d theta, that's 0. They're independent variables. It's simple as that. Do not read too much into this, okay? It's just independent variable. So r does not know theta, theta does not know r, unless you're talking about a trajectory in the polar coordinate. Then r and theta are both functions of t, in which case you still have this. In which case, unless you're talking about dr over d theta as this way, then it's non-zero. The partial derivative is always 0. Okay, the partial derivative dr over d theta is always 0, simply because they're independent variable. Okay, this is just a symbol. Okay, this is just a symbol. There's no inner product. There's no nothing going on. You just, okay. Do not read too much into this symbol yet. There's no additional structure being involved. Okay. Okay. So okay, we will introduce whatever setup later. Okay. So far this is just pure notations. Okay. So far this is just pure. There's no differential geometry whatsoever. It's just, so far it's just pure notation. Yeah, think of it as an indicator function, exactly. Okay. So yeah, you just think of this as something that saves us writing. Delta ij, something that saves us writing. Instead of writing dx1 over dx1 is 1, dx1 over dx2 is 0, and so on, as a big m by m matrix, you invent this symbol to save some writing. An inner product can be defined. Yes, inner product can be. You mean no? Inner product cannot be defined using delta ij alone. Inner product is a bilinear, symmetric, positive, definite bilinear form. A symmetric bilinear form. Delta ij is just a, I mean, given the inner product, you can define orthonormal basis using delta ij. Or you can put it this way: if you have a finite dimensional vector space and you have a basis, you can define the dual basis using that. But that's too much structure. This right now is just a symbol. Okay, it's just pure symbol. Okay, do not read too much into this. Yeah. There's no geometry, nothing going on. Okay, it's just a pure symbol. Delta ij is a Euclidean grand matrix, yes, but it can also be other things, right? Here is just a label. Okay, I will not continue on further digression. This is just a symbol. Okay. Anyway, let's look at a further example. Example 3. So let's say S is A alpha, X alpha. So A alpha, alpha lower, X alpha, alpha upper. The very first expression we introduced at the beginning. So let's consider differentiating S with respect to one of the X. Say, then we have partial S over X mu, partial F over X mu. I'm not ignoring. I already commented on it, right? So I just don't want to introduce extra geometric structure. So far, this is just a symbol. Okay, simple as that. It's just a way for us to save some writing. We're still in the preparation phase. There's no geometry going on. So this is A alpha times dx alpha over dx mu. Okay, here A alpha are assumed to be constants. Okay, they are not dependent on x alpha. Here, let me just emphasize, A alpha are independent of x mu. Okay. Otherwise, taking derivative would require product rule. Here, we don't worry about that. Okay, just treat all the alphas as constant, and then we just take the partial derivative of s with respect to any xi, an arbitrary x mu. Mu is a symbol. Okay, you typically don't use mu as an index in linear algebra, but it's quite common in tensor analysis to use Greek letters as indices. Okay, so therefore, this is just A alpha delta alpha mu. Right, from this formula. Okay, so far still nothing deep is going on, because if you write everything explicitly, s equals a1 x1 plus a2 x2 all the way to an xn, everybody knows ds over dx1 is just a1, ds over dx2 is just a2, and so on. So this little formula is just a way to package all n statements. Oh, sorry, old habit die hard. x2 should use a superscript. There you go. So this formula is nothing but a repackaging of this statement, of all n statements, just to save some writing. All right, let's continue. So here, what is this summation? Because you can actually sum this. You can actually sum this, because remember, this is the implied summation here. Alpha is repeated index. Upper, one's lower, one's upper. So it's just a mu. Okay, so just to keep things, just to re-emphasize why every equation holds, the first one is due to A alpha being a constant. You can take out the constant. The second equality is due to this formula we derived earlier. And the third equation is due to summation. Okay. In fact, sum of a delta symbol with another quantity is extremely common in tensor analysis. And I believe this is called a contraction, index contraction. Meaning one question. You said that partial derivative dxi over dxj equals 0, but the total derivative could not be 0. How can I see that again? The total derivative is this thing. The total derivative is, so let's use an example. Imagine, this is a problem in multivariable calculus, okay? Imagine you have a pond in the xy coordinate, x1, x2 coordinate. And in that pond, there is a temperature field. And the temperature field is visualized as level set. So imagine the pond is hotter here and cooler here. And now imagine you have a duck swimming in the pond along certain trajectory. And df dt is the rate of change, and also assume the temperature field is stationary. Okay, it does not change over time. So df dt is the total derivative. df dt, that's the rate of change of temperature that the duck experiences over time. Right? So in general, that's non-zero. Hopefully that's clear. But here we're talking about partial derivatives. Partial derivative simply says coordinate x1 does not depend on coordinate x2, coordinate x1 does not depend on coordinate x3, and so on. These are independent coordinates. And it has nothing to do with orthogonality. You can have a general curvilinear coordinate. So this is x1 constant. x1 constant are these families of curve. And x2 constant are these families of curve. It does not matter. It does not matter. Still, you have dx1, partial derivative dx1 over partial derivative dx2 equals 0 because they're independent coordinates. Yeah, so this is the curvilinear coordinate situation. This relation has nothing to do with orthogonality. It simply has to do with the assumption that x1 all the way to xn are independent coordinates. Okay. Anyway, enough on that. Well, of course, we'll see more and more examples, concrete examples later on. We'll work with actual coordinate systems with actual formula. So to reinforce everything we learned. Anyway, and now let's take a look at the next example. Remember, we encounter quadratic forms. And quadratic forms aren't just useful in geometry, they're super useful in statistics as well. The variance-covariance matrix arises from a quadratic form. So S equals A alpha beta, X alpha X beta. It's the same expression we've seen earlier. Alpha beta in A are lower indices, and in X they are upper indices. All right. So we want to calculate the partial derivative of S with respect to X. Okay, so how do we do that? Let S to be this format, and we will show that we show Aij, actually, sorry, if this is identically 0, if S is identically 0, then Aij plus Aj is 0. Okay, that's an interesting statement. That's an interesting statement. Okay. Interestingly, you don't need all the indices to be 0. Is that clear? You simply need this anti-symmetry property among the coefficient. So before we prove that, let's first get an idea of what is happening here. So imagine you just sum over n equals 2. Yeah, yeah. So it is true that Locke pointed out when you move along the coordinate system, the basis vector change. But still, you need independent coordinate component. Anyway, so here, let's say if you have, why is this true? So first of all, the square term must all vanish. Because let's say if you just have alpha and beta equals 1, 2, then S should read A11 x1 times x1 plus A12 x1 x2 plus, for example, okay, A21 x2 x1 and plus A22 x x2, x2. And this is identically 0. And for that, the square term must vanish exactly, because the square terms are non-negative. So this must always equal 0, meaning a11 must always equal 0. a11 must be identically 0. a22 must be identically 0 as well. And because x1, x2 is x2, x1. Okay, so here the coordinates are assumed to be real numbers, so commutativity holds, and those two must cancel. So that's basically the general statement. Aij plus aji equals 0. It must cancel. Okay, so how do we show this result using the index notation we learned so far? First, here's the proof. Okay, first let's differentiate with respect to xi, ds over dxi. Okay, so what do we give? What does that give us? Well, you need product rule here because xi and x beta is a product. You need product rule. A alpha beta is still considered as constant. So this is a alpha beta times x alpha times dx beta over dxi. Okay, so that's the first term, and then the second term you get a alpha beta times x alpha. Dx alpha over dxi times x beta. Okay, this is just the product rule. If you have doubt about this, simply write big S as the summation notation. Okay, and you can see, and you will see the summation notation is equivalent to this index form, to the Einstein notation. Okay, and now let's use the substitution. A alpha beta x alpha delta beta I plus a alpha beta delta alpha I x beta. Okay, so and now it's time to do the index contraction. So in the first summation, notice this is a summation. This is a summation. It's in fact a double summation. Alpha is summed over, beta is summed over, and because beta appears in the delta symbol, only the term with beta equals I has a non-zero contribution. So the first term just collapses to a alpha I. You just replace beta by I. A alpha I x alpha. Okay, so the beta now disappeared. And you do the same for the second. So in the second term, the only non-zero contribution is when alpha equals I. So you get ai beta x beta. X beta. So this is a linear function. And just to verify this calculation actually makes sense, a quick sanity check. Okay, let's do a quick sanity check because this is still new to us. Let's differentiate everything explicitly for the first for the alpha beta equals 1, 2 case. So let's do that just to verify our calculation is indeed correct. So verification n equals 2. So let's do ds over dx1. Okay, dx over dx1. So the first term, use a power rule. That's 2a11x1 right here. Then you have a12 x2 and plus a21 x2. And the last term Has nothing to do with x1, it's just 0. What's the argument about the vanishing a11 and a12? Because these two terms are non-negative, and this needs to be identically 0. Remember, S must be 0 for all x alpha x beta. Sorry, for all x, okay, for all variable values. For all variable values x1, x2. So here it says the equation on the left is identically 0 for all x1 and x2. That means the diagonal elements must vanish because these are squares. If let's say this is, so imagine if you have x squared minus y squared, this is not identically 0, no? This is not identically 0. Yeah, it is a polynomial indeed. It is a quadratic polynomial, homogeneous polynomial. Okay, got it. So let's check this is actually equivalent to what we've seen earlier. First of all, is there a summation over the first index of A? Is there a summation? Because let's check our formula. So this is a brute force derivation, a brute force differentiation. So what does A alpha I? We picked I to be 1 here. Notice here we picked I to be 1. So what is A alpha 1 x alpha plus A1 beta x beta? What is that? Well, apply the summation convention. This is just A 1 1 x1 plus A 2 1 x2. That's the first term. And then the second term expands to A11 x1 plus A12 x2. Hold on a second. Why? How come? My bad. Hold on. The first term expands to A11 x1 plus A21 x2. Yeah. The second term A1 beta x beta, beta from 1 to 2, that's A11 x1 and A12 x2. Oh yeah, there's nothing wrong. Everything is correct. But because you have these two terms combined to 2 times A11 x1. So it works out. This is the same term, and this is the same term. Okay, so it works out nicely. Indeed, sanity check confirmed. So now, okay, and now we keep differentiating this one. So that's the first derivative. And by the way, this is also useful in statistics and machine learning because often you want to differentiate matrix valued, or you want to differentiate matrices, matrix calculus. In fact, matrix calculus, there's a course. There's a course on matrix calculus in MIT OCW. It gives you a lot of practice for this stuff and its application. You know what? I should probably give a link for that. Hold on. MIT OCW matrix calculus. Yeah, it's called matrix calculus for machine learning and beyond. You do a lot of things we just described there. I'm not sure if they use the same index notation, but it is very useful. Okay. I wonder if there's a way to do it without differentiating, since it looks like there could be an argument by symmetry. Yeah, I'm pretty sure there is, but the purpose of this study is to practice index notation. That's the main point. This stream is golden. Thank you so much for in Algeria. No worries. No worries. So yeah, so basically what we did there is consider standard stuff. in matrix calculus for machine learning and beyond. I will put this link in chat, and also there's videos on YouTube. So pretty awesome. Okay, so for those who are interested in machine learning. Okay, enough digression. Let's continue with the calculation. So what's the second derivative? Anyway, here, second derivative. Of course, I mean the second mixed partial derivative. So you have ds over d square s over dxj dxi, like this. Basically, that's the Hessian matrix. This is a Hessian matrix. The first one is the gradient vector. But actually, the gradient vector is a notion that needs a little bit of a correction later on. Okay, as we shall see, gradient is not really a vector, but rather a covector. Gradient is most appropriately understood as a linear functional rather than a vector. It's just because there is this duality in Rn that you can consider it as an actual vector. But here in multivariable calculus, we treat gradient as a vector. But in tensor analysis, it is rightfully considered as a covector due to the different transformation law it satisfies compared to ordinary vectors. Okay, but here we're talking about the Hessian matrix here, ds squared over dxj dxi. Of course, by definition, this is just d over dj, d over dxj of ds over dxi. And let's just plug in the expression of ds over dxi right here. So this is use the fact that, actually let me just plug in the expression first and then distribute the operator. A alpha I times x alpha plus a I beta x beta. Okay, distribute the operator, you get a alpha I d x alpha over dxj times a I beta dx beta over dxj. All right, and then use the Kronecker delta representation. This is a alpha I times delta alpha j plus a alpha beta, a I beta, delta beta j. Okay, and then sum over repeated indices. Hold on a second, is there any repeated indices? Yes, in the first term, alpha is repeated. So only the index alpha, only when alpha equals j, there's a non-zero contribution, you get a ji. The first summation gives you aji, and the second summation is just aij. Okay, and because s is constant 0, this must be 0. I'm going to Eigenkris's introduction in this month. Would be highly recommended. Exactly. Yes, Eigenkris is amazing. Eigenkris is amazing. So, his, I mean, like his prepared videos are infinitely more informative than I'm doing here. Okay, Eigenkris is a physicist as far as I know. So it's great for geometric intuition, exactly. And he give examples with actual numbers, so it's even greater. Okay, so what I just mentioned earlier, the notion of vectors and covectors were explained perfectly there. Strongly recommended. Okay, anyway, so this is what we, there's tons of actually great resources on tensor stuff just on YouTube. Okay, anyway, here. So therefore, aji plus aij is 0. Oh, okay, remember, even though I and j are repeated in this expression, there's no summation going on. Okay, caution. Okay, this expression star is just an abbreviation for how many equations? That's an abbreviation for 9 equations. If let's say n is equals 3, if n equals 3, I mean, you know what? Let's not even assume n equals 3. That's an abbreviation of n squared equation. Just a shorthand. For example, if n equals 3, actually n equals 2 is enough. If n equals 2, this means a11 plus a11 equals 0. You see why the diagonal elements must vanish? And then a12 plus a21 is 0. a21 plus a11 is 0. Sorry, a12 is 0. And lastly, a22 plus a22 is 0. That's it. Yeah, it becomes opposite nice when you compute all those components. Exactly. Exactly. So, this whole business of tensor analysis is because of analytic geometry, right? When Descartes invented analytic geometry, it was such a massive breakthrough because previously difficult theorems can be shown just using a straightforward algebra. Before Descartes, everything was done synthetically. No coordinate system. You push the axioms and theorems in Euclidean geometry to get your results, and it takes a lot of skill. So analytic geometry was the first attempt towards the what we say automation of theorem proving, which is awesome. But then again, introducing coordinate system introduces extraneous information. The coordinate system has nothing to do with the geometric property that you wish to prove. So sometimes you obtain a result, you have no clue whether this is an artifact of the choice of the coordinate system or is an actual geometric meaningful quantity. So tensor analysis was introduced to explain that to get around that problem. Of course, we want the geometric insights as much as possible, and perhaps that's the reason why modern differential geometry prefer to use index-free notations. But when it comes to actual concrete problems, coordinates are still unavoidable. So the eventual goal is to master both aspects. It's like in linear algebra. You of course need the fundamental skills of working with matrix multiplication and whatnot. Okay, all sorts of actual computational tools. But it also helps if you have a more abstract perspective, right? The linear algebra of abstract vector spaces and linear transformations, right, in which you sometimes avoid working with coordinates at all. Right? So there are advantages and disadvantages of each approach, of course, and they complement each other. They're not enemies. Yeah, synthetic is definitely harder, but a lot of fun. Exactly, and you have to think about, okay, some sort of fancy constructions, which can be highly non-natural, right? But anyway, that's a skill. It's more of a it's also it's a science and an art at the same time. So anyway, let's continue. So here we can define the generalized Kronecker delta as follows. So you can have more than two indices. Generalized Kronecker delta. And this is where things can get a little bit nasty. So as we shall see, the definition of tensor in classical tensor analysis has tons of indices. I think it was Hermann Weyl, German mathematician, disparaged the tensor calculus as orgies of indices, something like that. So this is a generalized Kronecker delta. It says the superscript and subscript can have any value from 1 to n. So I1, I2, all the way to IM, J1, J2, all the way to Jm are all in 1, 2, all the way to n. This is a generalized Kronecker delta if at least two superscripts or at least two subscripts have the same value, or if the superscripts are not the same set of values as the subscript, then we define the generalized. Actually, you know what? I'm just going to give a screenshot here. I think that's not enough for me to get demonetized. Okay, so it says if at least two superscript or at least two subscript have the same value, or if the superscript are not the same set of numbers as the superscript. Hold on a second, what does that mean? Then we define the generalized Kronecker delta to be 0. If at least two superscript or at least two subscript have the same value. Or if the superscripts are not the same set of numbers as the subscript, then we define the generalized Kronecker delta to be 0. If all the superscript and subscript are separately distinct, and the subscripts are the same set of numbers as the superscript, the delta have the values of +1 or -1. Hold on a second, it can take -1? Okay, you know what? I'll just put the relevant text here. Okay, so let's help decode this piece of text together. Okay, here you have some examples too, which is helpful. So it says, if all the superscript and subscript are separately distinct, and the superscript are the same set of numbers as the superscript, the subscript are the same set of numbers as the superscript, the delta have the values of +1 or -1 according to whether it requires an even or odd numbers of permutation to arrange the superscript in the same order as the subscript. So let's take a look at these examples. So delta 1, 2, 3, 1, 2, 3 is 1. Why is that? Because all the superscript and subscript are separately distinct. Right? See, 1, 2, 3, 1, 2, 3, these are all distinct. And of course, the superscript and the subscript are the same set of numbers. 1, 2, 3, 1, 2, 3. Okay. It is equal to 1 according to whether it requires even or odd numbers of permutation to arrange the superscript in the same order as the subscript. Well, 1, 2, 3, 1, 2, 3 are identical, so you need 0 permutation. 0 is an even number, so it's equal to 1. That's the first example. Okay, and now you have delta 1, 2, 3, delta 2, 3, 1. Delta 1, 2, 3, 2, 1, 3. That's a -1. Why? Because to arrange, let's arrange the superscript to the same order as the subscript. You do what? You exchange 1 and 2. That's just one permutation. So it's a -1. Okay, and the third example, delta 1, 2, 3, 2, 3, 1 is 1. Why is that? Well, because you need 2 permutations. So for example, of course, the operation order is not unique. You can first exchange 1, 2. So 2 is now at the front. And now exchange the order of 1, 3. So you get 3, 1. So that's 2 permutation. So equals 1. Do you know why they are -1? Here is this is the rule. Because you need an odd number of permutation. See, 1, 2, 3. Is it 1, 2, 3? To get 2, 1, 3, you just exchange 1, 2. That's just one permutation. So that's -1. All right, and the last example of the first row, delta 173, delta 173 and delta 163 is 0. Why? Because of the first sentence. The superscript, if at least 2 superscript or at least 2 subscript have the same value, or if the subscript are not in the same set of numbers. Exactly, that's why the superscript are in the set 1, 7, 3, and the subscript are in the set 1, 6, 3. They're not the same set. If the subscript are not the same set of numbers as the superscript, then we define the Kronecker delta to be 0. So this is 0, that's why. Okay, and here, delta 1, 3, 4, 8, 1, 4, 3, 8 is -1. Why? Because only 3 and 4 are exchanged, one permutation, so -1. Next, delta 1, 2, 2, 1, 2, 3. That's a 0. That's a 0 actually for 2 reasons. First, because on the superscript you have two twos. Okay, here it says if at least 2 superscripts or at least 2 subscripts have the same value, 2, 2, then that's 0. Another way to see it is because 1, 2, 3. In fact, you can ignore the lower index. You can ignore the lower index. Simply looking at the upper index is enough to see this is 0, but then you have a different set of numbers on both the superscript and the lower script, so that's a 0. Okay, second term for exactly the same reason. The third term is because the superscript and the subscript are not in the same set. Actually, you know what? That's BS. That's BS. Oh, that's true. That's true. In fact, because on the subscript, the set is 2, 3, and also 3 is repeated, so that's a 0. So that's a 0. In fact, delta 1, 2, 3, iij is 0 because of repeated I downstairs. Okay, so hopefully we think we can understand this definition now. So there are 2 parts of the definition. First, when it is 0 and when it is 1. 1 or -1. This is that the Levi-Civita symbol? Guys, help me out. If you guys know anything about this, it feels to me like in the Levi-Civita symbol that defines the cross product. Is that how you spell it? Question mark? But you know what? That's okay. We'll just continue pushing because now we understand the definitions here, and we define the symbol. This is epsilon. Yeah, that's the Levi-Civita symbol. Okay, great, awesome. Thank you so much, Lockheed. So epsilon I1, I2 all the way to IN is defined as such. Is defined as such. So let's think about what does this mean. What does this mean? It means that if you have two repeated indices on the left-hand side, it's immediately 0. Right? And if you have, say, so if it takes even number of permutation to turn I1, I2 all the way to IN into the order of 1, 2 all the way to n, if you need even numbers of permutation to do that, then you simply get 1. Okay, and otherwise, if you need even numbers, or if you need all numbers of permutation to turn the sequence I1, I2 all the way to IN into 1, 2 all the way to n. Okay, the operative word is odd number of permutation, then it's minus 1. So let's do some examples here. For n equals 3, example. It's not in the text, but I figured it's important to work this out. So let's say n equals 3. What is epsilon I1, I2, I3? So in total, there should be 27 numbers. So it should be 27 numbers. Let's group them into 3 values. All the zeros, all the ones, all the minus 1. Okay, so all the zeros, these are easy because you just need 2 repeated indices. So let's say you have epsilon. Actually, you know what? Let's do it in a more organized way. You have 27 values. So here, this is 1, 2, 3. This is 1, 2, 3. So you know what? Let's just consider the non-zeros. Let's just consider the non-zeros. What are the non-zeros? Suffice it to consider the non-zeros. So let's think about the even and odd permutations. So how many permutations are there, first of all? 6, right? 3 factorial equals 6. So it's 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 1, 3, 3, 2, 1, 3, 3, 1, 2, and 3, 2, 1. Okay. All right, so this is a table. So these are I1, I2, I3. And we need the values of the epsilons. Which of those are non-zero? Sorry, I mean, they're all non-zeros, but what's the 1 and minus 1? So the first one is simply a 1. It's in the same order as 1, 2, 3. Okay, so the second one is minus 1 because you need to exchange 2 and 3. That's odd number of permutation to get 1, 2, 3. So that's a minus 1. What's 2 and 3? Well, 2 and 3, for 2 and 3, you need 1 permutation to get back to 1, 2, 3. So that's a minus 1. What's 2, 3, 1? That's 2 permutation, which is 1. What's 3, 1, 2? 3, 1, 2, 2 permutations. Right? 2 permutations. Think about it. So you from 1 to 3, let's say you have 1, 2, 3. Here, 1, 2, 3. You first exchange, you want 1 in the middle. You see, the thing is 2 numbers moved, okay? Kind of that way. So you can you exchange 1 and 2, so it becomes 2, 1, 3 like this, and then you exchange 2 and 3. So that's two permutation. That's a 1. And lastly, you just need to exchange 3 and 1 to get back to 1, 2, 3. So that's odd permutations. That's a -1. All right. Helpful thing to know, maybe you can prove this later, is that a cycle rotation of odd numbers of indices will always be an even permutation. Yeah. I'm not sure if I will get into that, but definitely the permutation is worth studying on its own. It's an important subject in abstract algebra. Yeah. So now we have this generalized Kronecker delta is now defined. Okay. So now we have. We will do the exercise later. We'll try to proceed with the main material. Okay. So far we understand it. I think we understand everything. Next, let's look at the next topic called determinant. The determinant is a good exercise with working with Levi-Civita. We determine the determinant. We define the determinant by the following equation. So let's write that down. So let's say you have a double-indexed array Aij. Okay, so Aij, taking the determinant. The determinant is defined as follows. I assume everyone here has already seen determinant before, okay, in linear algebra. But here we're just going to repackage everything into the symbols we defined earlier using the same summation notation. So this is defined as epsilon. Hold on a second. Epsilon downstairs, I1, I2, I1, I2, blah, 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 and so on to In. And then A1, A1I1, A2I2, all the way to ANIN. There you go, right? So this is a determinant, and it is also can be defined as the Levi-Civita symbol, epsilon with upper indices I1, I2, all the way to In. Okay, and then I1 upper index, 1 lower index, and then I2 upper index, 2 lower index, all the way to AIN upper index and N lower index. Okay. The reader should know that this definition agrees with the definition of the special case of second and third order determinant which he has encountered in elementary algebra. The definition of a determinant as given by here shows that it consists of a sum of terms of n to the n numbers. Exactly, because in one repeated index, oh, actually, this is nonsense. This is messed up. My goodness. My goodness. So, the equation above should have upper index I1 all the way to In here. Sorry, guys. Yeah, this is still kind of painful to write, right? Perhaps that's why Sheldon Axler hates determinant. Anyway, so here you have the two expressions for determinant, and it has n times n terms. N to the n, not n times n. They're n to the n terms. So it grows extremely fast. Of course, a lot of them are 0. And in fact, only n factorial terms are non-zero. Just like in the analysis for the n equals 3 Levi-Civita symbol. Right? So in general, we know there are 27 terms. 3 to the 3. In general, there's 3 to the 3, 3 to the 3 values in general, entries. So 27 entries in total. 6 of them are non-zero. Right? So that's why I just decided to only write down the non-zero entries. Okay, so there's that. Here, in general, of course, you have n to the n terms, in which n factorial terms are non-zero. All right, so that's the determinant. Each term consists of a product of elements, exactly, and one element from each row and column. So if you write down the full matrix, then, for example, let's do the 3 by 3 determinant, n equals 3. Okay, if n equals 3, then the determinant of aij would be, yeah, just use what we have earlier. So all the positives are 1, 2, 3, a1, a2, a3. These are the positives. Okay, a2, 3, 1. Oh, not a2, 3, 1. That's terrible. a2, a3, a1. And lastly, a3, a1, a2. And all the minus signs are minus here, minus a1, a3, a2, minus a2, a1, a3, and then minus a3, a2, a1. No? Right? So that's the full expression for n equals 3. And as you can see, oh, actually, this is terrible. My God. Okay, I think I messed up something. I missed the upper index totally. Okay, so here it should be 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, so now it's fine. That's the upper index. Okay, so for all these terms, so for all n to the n terms, in the first expression, the upper indices are all, that's one term, all 1, 2, all the way to n. Okay, so in a matrix a1, 1, a1, 2, a1, 3, a2, 1, a2, 2, a2, 3, a3, 1, a3, 2, a3, 3. It says in each term consists of a product of elements, one element from each row and column. So for example, a11, a12, a23 are these elements. The point is, each row for a given term, it must only consist of factors that comes from exactly one element from, I mean, my goodness, I can't phrase things properly, but basically, for each given term, you can locate the factors in this matrix, and their position should have the following property. If you look at each row, there should only be one element being selected. If you look at each column, again, only one element should be selected. Yeah. All right. So here, let's continue. It says in the text, since I1 and I2 are dummy indices, you can interchange them. Okay, so let's write that. Since I1, I2 are dummies, since they're dummy indices, then you have Aij determinant equals, let's use the second representation because for no particular reason, just use the second expression. You can interchange the order of I1 and I2. So let's just do that. I1, I2 are now reversed. Here on the right, we do the same. So these are just labels. Okay, they don't affect the value of the determinant, the summation. Okay. It says, and then it says, an interchange of the subscript 1 and 2, however. The interchange of a subscript 1 and 2, however, will mean an extra permutation will be needed in I1, in I2, I1, I3. Actually, you know what? Perhaps I should probably make a screenshot and put it here. So this is what we're doing is we're trying to show that if you interchange the say two columns, if you interchange two columns here, the lower script stands for the column. If you interchange two columns in the determinant, then it picks up some minus sign. And it pick up a minus sign. So that should be understandable because interchange in a subscript 1 and 2, however, will mean that an extra permutation will be needed on this sequence, I2, I1, I3. On the right, if you interchange, say, 1 and 2, here, if you simply change the dummy index, nothing happens. Interchange the dummy index, nothing happens. If you change 1 and 2, then an extra permutation will be needed on I2, I1 all the way to IN. This changes the sign of the determinant. Hence, interchanging two columns or rows changes the sign of the determinant. So that's what we're getting at. So that's the point of this exercise. The thing is, the idea is you can prove properties of determinant using the index notation. I mean, there's nothing special about index notation. It just simplifies the writing. That's it. Okay. An immediate corollary is that if two columns or rows are identical, then the determinant is 0. I think the text intends to swap I1, I2 at the bottom, but not the one on top. Actually here, it doesn't matter. It doesn't really matter. I will show you the text. Okay, sorry. I didn't do any change myself here. Okay, so that's the text above this part. Okay, let me just okay, my bad. Yeah, that's the original text. So you see, I1, it doesn't really matter here. It means if, let's say, if you have 1 to all the way to n downstairs, that means you're fixing the column indices. Then you see here the summation indices I1, I2, IN. In the matrix, it represents the row indices. So you know it's like in determinant calculation, you can sum over, you can expand with respect to row or expand with respect to columns. It does not matter. So yeah, You either fix all the upstairs or you fix all the downstairs. So here in this example that I made up, okay, I'm using epsilon. I'm using the, hold on a second. Yeah, I'm using epsilon ijk a1i a2j a3k. I'm using this formula here. So I fixed all the upstairs to be 1, 2, 1, 2, 3. It does not matter. You can do it both ways. I struggle with intuition about abstract. How do you improve that? Well, find concrete examples whenever possible. Okay, it helps a lot. And ask questions. We have a Discord server. Go ahead, and a lot of people are very eager to help you. So yeah, indeed, a lot of abstract mathematics are not there. I mean, of course, there are years, if not decades, of work, results of years and not decades of work. It's not supposed to be easy. It's just the way it is. It's totally natural. Anyway, so here, let's continue. Now the goal is to prove another property. I think has to do with what? Okay, actually I have no idea, but reading this is very painful. So let me just paste down the text here and let's try to summarize. Okay, so next that's the preceding paragraph. So let's now examine the sum b j1 j2 all the way to jn. Okay, I'm not sure if everyone can see this clearly because there's a lot of small indices going on. Okay, let me just zoom in and enhance. So let's now examine this sum. Let's now examine the sum b of j1 j2 all the way to jn equals the Levi-Civita symbol epsilon I1 I2 all the way to in times this product here. Okay, I know, right? I know, but okay. But the point is, we know what this means, right? We know what this means. So here, J1, J2, all the way to Jn, these are considered as free indices. These are free indices. They're not summed over. I1, I2, all the way to In are summed over. It says, if J1, J2, all the way to Jn takes on the values 1, 2, all the way to N respectively, by the way, this does not mean J1 equals 1. Okay, J2 equals 2, and so on. It just means that J1 all the way to Jn lives in the set 1, 2, all the way to N. If this is true, we know that 475 reduces to 470. We know that 474. What's 474? Hold on a second. What's 474? Well, 474 is just this definition. It's just the definition of determinant. This is 474, by the way. Hold on a second. Why is that? Oh, it means the particular order you fix, say the upper stairs or the upper indices or the lower indices don't matter. Pro tip: make text unreadable to avoid AI reading it. You mean the AI system that does the DMCA? I don't think this is on, so to say, this is infringement. Okay, because I'm adding extra commentary to it. Like what else am I supposed to do? I guess the localized showcase of particular books are okay. Anyway, so here avoid AI reading it. So it's like you don't want AI to be trained using your stuff. Okay, anyway, so it doesn't matter. Okay, so let's come back to this paragraph here. So if J1, J2 all the way to Jn takes some value 1, 2, and n, but not respectively. What do you mean not respectively? Then we have interchanged the roles. Oh, respectively means 1, 2. Okay, actually, I misunderstood the sentence. If J1, J2 all the way to Jn takes on the value 1, 2, and n respectively, that literally means J1 is 1, J2 is 2, and so on. Then, of course, this is the same as the original definition, no problem. But let's say if they takes on the values but not respectively, then you have interchanged the roles. I suppose you need to add the extra assumption that there's no repeated indices. That is to say, J1, J2 all the way to Jn is a permutation of 1, 2 all the way to n. That means you've interchanged the role. So I think this should be better rephrased. This should be rephrased as if J1, J2 all the way to Jn are a permutation of 1, 2 all the way to n. Exactly. And even permutation reduces 475 to Aij, and all permutation reduces to minus. Okay. If two of the j's are the same value, then it's 0. Okay. So that includes the situation where you have a non-injective map between 1, 2 all the way to n and J1, J2 all the way to Jn. Companies do not need the help, but this is a topic that has strong feeling as I will not continue. Okay. Yeah, they steal your shit, don't you? And steal your job. Anyway. So okay. And hence you have the following. Hence we have the following. So in this formula, here you have the okay. So this is a perhaps we'll be using this later. Perhaps we'll be using this later. So if you say have an Levi-Civita symbol epsilon I1, I2 all the way to In times AJ1, AJ1, I1, AJ2, I2 all the way to AJN, IN. What you get is the determinant. Times the Levi-Civita symbol, but the indices I1 all the way to In are swapped to J1 all the way to Jn. So, and by the way, if you're suffering right now, reading this stuff, I don't think this is terribly relevant to the main goal, which is which we were trying to accomplish. That is the curvature part. But I don't know, actually. I don't know whether this is going to pop up to be super important, actually. I retract that comment. But basically, this formula is useful for simplifying the left-hand side. So that's a determinant. And then on the right-hand side, you still have the Levi-Civita symbol, but now you just swap the indices to J1 all the way to Jn. Okay. Okay. And there you go. Here, and the position of the indices are the same. Position is still, this is the upper index, here is the upper index. Of course, I don't think it would affect the values. I don't think here, let's say, because right now we still haven't assigned particular meaning to upper and lower indices. I think it's just a matter of aesthetic taste, that you keep the indices up, because on the left you also have upper indices. If you read, yeah, physics engineering still pretty much uses vector and tensor analysis. Not everybody is on the same page when it comes to formalism. Okay, and as applied mathematician, you need to be bilingual. It's just the way it is. Okay, applied mathematicians are the ambassadors of scientific communication. Okay, when you live in Rome, you do what the Romans do. Okay, you can of course advocate your particular choice, but most often you need to meet other people halfway. Okay, mathematical research is fundamentally a sociological phenomenon. Okay, it is. I mean, the process of doing so is often solitary, but at the end of the day, you will need to communicate your result. It is not important for you as an individual to appreciate a particular discovery. You have to communicate to others, otherwise it just gets lost. Right? For that, we need communication. So there's different notations and whatnot, and you can argue endlessly about their respective advantage and disadvantage, but this is the nature of research. Translating notation is part of the work. Okay, so here I think we understood this part of the text. So these are used for formula. Let me just place it on the side, and we will place this part on the side, and we'll circle this two formula. These two. I think they will come in handy later when it comes to simplification. Yeah. All right. So that's cool. So let's do an example. We're going to prove the multiplication rule of two determinants. Right? So example. So we all know from linear algebra the determinant of A and B, A times B, okay, is determinant of A times determinant of B. Can we prove this? Let's go. So there you go. Let's continue and prove this theorem. Proof. This is example how many? I lost track. So here we have example 4. This is example 5. This is example 5. Proof. Okay, let's prove that. So first, let's start from the right-hand side, shall we? So Aij determinant times Bij determinant. Okay. So let's say you have, how do we cook this up? Let's just use the definition. So Aij determinant is here, and Bij determinant is, you can use definition in terms of the Levi-Civita symbol. So epsilon I1, I2, all the way to In, times B I1 upstairs, 1 downstairs, Bi2 upstairs, 2 downstairs, all the way to Bin and N downstairs. All right, so there's that, and use this property. See, we can use 475b. Using 475b, you can combine the first two factors. Here I've just used the definition, for b, Bij determinant. Okay, and now the first two factors gets combined, look at the formula. That's the Levi-Civita symbol, epsilon j1, j2, all the way to jn, aj1, aj1, I1, aj2, I2. Yeah, I'm using here. This is the formula. It's just that in 470, actually, you know what? Let's rewrite the first step so that it conforms to the right hand side of 475b exactly. So everything is completely clear. So you don't need to do the mental swapping of I to j anymore. So yeah, there you go. It doesn't matter. So I'm just going to change all the indices in the first step into j1 all the way to jn. Okay, and this way you get here, and here this way you get just I. This is 475b. So it's epsilon I1 IN all the way to IN, and then A I1 J1, AI2 JN, sorry, J2 all the way to AIN JN. Okay, and then BJ1 1, BJ2 2, all the way to BJNN. Okay, cool. So what do we do now? Well, you can combine the terms. Let's group the terms. Group these two together. So this way, you can create a matrix multiplication. Yeah, I think it was Christian who mentioned earlier that a matrix multiplication is also a great exercise for understanding the summation notation, and here we go. It comes useful. So AI1 J1 is going to be grouped with BJ1 1. Okay, and then AI2 J2 gets grouped with BJ2 2. And you do this until the last pair, which is AIN JN BJNJ, BJNN. Okay. So this is just the same Levi-Civita symbol, epsilon I1, I2 all the way to IN, and then C1J1, C2J2, oh, sorry, C1I1, yeah, CI11, CI22, all the way to CINN. Where Cij is the summation AI alpha B alpha J. And this is essentially matrix multiplication. This is essentially a matrix multiplication. So therefore, as you can see, this fits the definition of the determinant of Cij. Of course, and this is equivalent to the determinant of AB is determinant of A times determinant of B. So that's pretty cool. Because usually in linear algebra, showing determinant is multiplicative takes a little bit of work. If you want to avoid a heavy summation and a permutation argument, you can use that. You can actually, in most texts, I believe, you prove the property of the multiplicative property of determinant using so-called elementary matrices. Right. Elementary matrices is equivalent to Gaussian elimination. So basically there you decompose a matrix into a product of elementary matrices, and then you first prove the multiplicative property for elementary matrices, which are very easy to verify. They're just three types of elementary matrices. Elementary operations applied to the identity matrix. And you can verify the multiplicative property for elementary matrices rather easily. And then you say, oh, because of, and then you apply an induction argument. You apply an induction argument because a matrix is always the product. The matrix is always the product of an elementary matrix and its REF. And if a square matrix is invertible, its REF is always the identity matrix. So it just becomes a property. It just becomes a proper product of elementary matrices, and you're done. So it was proved in a rather indirect way, and in elementary linear algebra. Actually, perhaps what I just described might be a little bit terminology heavy. Let me just give you guys an example of what I was talking about. How the multiplicative property of determinant is usually proved in elementary linear algebra. Here I have this great resource, Linear Algebra 1, a module run by University of Waterloo. Here, if we go to determinant, see determinant and row operation, probably here. The determinant is defined recursively as the cofactor expansion. Of course, that's completely valid. What happened to the part? Okay, I'll answer the question shortly. Okay, I just wanted to give an example of how the multiplicative property is usually proved in linear algebra. We go next. Yeah, determine an elementary matrices. So this is usually how it's done. An elementary matrix, E is E. Determinant of EA equals determinant of E times determinant of A. And then you use the fact that the REF is a product. The REF is a product of elementary matrices and the A itself. Okay, and then you use the property that we've done earlier, and finally you reach the determinant of A equals determinant of A, determinant of AB equals determinant of A times determinant of B. It saves you heavy writing by taking this rather indirect route. Of course, that's totally valid. Okay, but here what we're doing is essentially a direct proof, but with the help of index notation. Marco asked, what happened in part AIJE? Oh, what happened here? This is what happened because we used the formula 457b. And the justification is above. Yeah, so you see, both rules are totally valid, right? So, and this one is more direct. Okay, so let me just use a different color to highlight what we did. Those two are the same. You got it, Marco? Okay, so now let's take a look at the next example. Of course, I already mentioned that determinant can be defined using cofactor expansion. And the notes will be uploaded, by the way. So the next example is cofactor expansion. So we just wanted to show the equivalence of the definition we give earlier and cofactor expansion. So let's start with the definition, Aij. Determinant. Aij determinant is the Levi-Civita symbol, epsilon I1, I2, all the way to In. Yeah, because, I mean, these formulas are not easily digestible at first, but so that's why I quoted the result here, 475p. That's because, okay. Anyway, so, and the definition. And here, this is the definition again. Okay, this is what we call a two-column proof. One step, one justification, except the ones that are obvious. Okay. Anyway, so let's start with the definition. Determinant equals the Levi-Civita symbol AI1, 1, AI2, 2, all the way to AIN, N. All right? So what we do now is we're going to isolate a factor, say AI1, 1. Okay? AI1, 1. So don't worry, we'll actually do an explicit example to illustrate what is actually done here. So I1, I2 all the way to, oh actually I1 here, I1, I2 all the way to IN times, okay, AI2 2 all the way to AINN. All right. So this is, we can write it as, because you see I1 appeared twice, of course, all the I index stuff. This index stuff is a Leibniz formula. I'm not sure Leibniz. There's so many things named after Leibniz. I don't know if I'm pretty much certain that Leibniz made a contribution to determinant. Yeah, this is the Leibniz formula that Vernon is talking about. Very likely. Yeah, very likely. Okay. I hate to. I apologize if it sounds nationalistic, but whatnot. Determinant were discovered by Chinese centuries ago before the Europeans did. Okay. When it comes to actual calculation, okay, these are already discovered by the Chinese, but perhaps not in as actual proofs. Okay, so there's that. Right. Anyway, it doesn't matter. I'm not salty or anything. So this is can be written as A alpha 1, A 1 alpha. Let's write it as A1 alpha. Let's write simply as a notation. Where A1 alpha, that's the cofactor. A1 alpha is epsilon alpha. I just changed I1 to alpha, that's it. Epsilon alpha I2 all the way to IN, AI2 2 all the way to AIN, N. Okay, this is called the cofactor of A alpha 1. It's the friend of A alpha 1. Yeah, not just Chinese, but also Islamic and Indian mass contributions. But enough of that. Okay, I'm not salty or anything. Okay, the main focus is still the mass itself. So here, this is called the cofactor. Let's, of course, let's take a look at an example of how that corresponds to the usual linear algebra notation. So we know the 3 by 3 case. For example, we have the 3 by 3 determinant formula. There you go. Oh, here. Actually, let me change the color. Sorry, didn't copy that. Okay, I just wanted this part. I just wanted this part. So let's try to isolate the cofactors. Yeah, it kind of I'm a little bit amused that mathematician who fought for priorities and whatnot, right? The Europeans are, I mean, it's not European mathematicians are, especially in the early modern time, were very jealous about who gets the credit and whatnot, right? So you're always welcome to write a text where you provide attribution to history and add that to the record of books. Yeah, it's been done, and it's been gradually more appreciative. Okay, so anyway, so here let's figure out what is the cofactor of alpha 1 1, alpha 2 1, and alpha 3 1. Right here, we should have three terms. Because alpha is the index, it runs from 1 to 3. You should get alpha 1 1 times something. No, not alpha 1 1, but a 1 1 times something. Okay, plus a21 plus times something, and then a31 times something. Okay, and then let's just locate the cofactors. So a22, a33. We'll identify the cofactors from the original formula and then check with the new definition, see if they are actually the same. Okay, and then minus minus a23. That's a 2 by 2 determinant, right? Yeah, exactly. Exactly. So in fact, you can just see the grouping right here. Use a different color. You can just see the grouping. It's just right here. Okay, just split it here. Okay, that's the grouping. Oh, actually, A12, yeah, A12. Oh, not really. A12, where's A12? Actually, I need A21, huh? I need, yeah, A11, A21, A31. Oh, I think it's okay. I think it's okay. I think it's okay. A21, yeah, A21 times, no, it's messed up. It's not the right order because H1 is here anyway. So let's rewrite, but that's okay. Not a big deal. A21 times A13, A31 minus A2, A21 is here, A21. Hold on. It feels weird. A21. Is that a mistake here? Third and fifth term. Third and fifth term. I know, but are they messed up? Oh, actually, here, never mind. Vernon, you're right. Yeah, third and fifth term. A21 times A13, A32. Yeah, that'll be right. And then minus A32. My God, can't write. And minus A12, A33. Yes, that's correct. Yeah, that's correct. 3223. Okay, great. And then finally, perhaps it is better. Okay, actually, you know what? Perhaps it is better to put a minus sign for the second term. That's usually how we write it in linear algebra, right? 2, 3 minus 3, 2. Okay. And lastly, you have A31. Right? A31, A31, A21, A32 minus A22, A31. Okay. So that's good. That's good. That's good. So this should be, in our notation, this should be A11. And this should be A12. This should be A12, and finally this should be A13. Let's check. Right, let's just check A11, for example. That should be enough. A11, by definition, by the definition above, this should be the Levi-Civita symbol, epsilon 1 here, epsilon 1. And then there should be two indices, because in total you have, it's just, I'm just going to say JK, okay? Yeah, say JK. Typically in 3D you write epsilon IJK. And then you have a hold on a second. So the lower indices are supposed to be fixed, huh? I think I didn't use the right expansion. So here in this expansion, the Levi-Civita symbol is downstairs, but I use upstairs. That's kind of messed up. Okay, I can't use this. I expanded in a different way. Okay, so yeah, that's unfortunate. I can't do the verification now just by using that result. Okay, so you know what, guys, I'm going to erase this. Okay, I'm just going to erase this, and I apologize, but I'm going to leave it as an exercise. Exercise, verify A11, A12, A13 holds even is are agree with the usual definition. In linear algebra. So basically, if you say expand the determinant this way, so let me write that down real quick. Actually, you know what, this is bad. A11, A12, A13, upper, lower. So let me just write the answer here, okay, and you can do the verification. Okay, cool. So now you have the 3 by 3 determinant, and we are expanding according to what? According to, we need A11, A21, and A31. So that's Is that the row or a column? That's a column. So you're expanding with respect to the first column. So the usual definition in algebra of cofactor expansion is as follows. You erase the column and row containing A11, and you calculate the determinant of the 2 by 2 matrix. Okay, so that's A22, A23, and of course when it comes to cofactor, there's this sign factor as well. In linear algebra, you look at the sum of the indices, say A11, and that's a even number, so you get a plus sign here. And if the sum is odd, say A21, you pick up a minus sign. There's a minus sign here. Okay, erase the column and row, and you should get A12, A13, A32, A33. Okay, and lastly, the last factor, A31, has a cofactor of A12, A13, A32, and A33. There you go. So yeah, so this basically you need to verify A11 according to the definition above is indeed this 2 by 2 determinant. Okay, that's a nice exercise too, as a sanity check. Okay, so that's the definition for the cofactor. So in general, of course, here we only extracted the first factor. You can do this for any particular factor. In general, you should have the general factor, cofactor expansion. In general, Aij determinant is this say well, pick a particular A you wish to factor. Let's call that A alpha beta. A alpha beta, okay, and then times epsilon I1, I2, all the way to In. Well, of course, one index is actually no index is missing. No index is missing. And then, but one of them needs to be swapped to alpha, I believe. One of them needs to be swapped to alpha. So AI1, 1, all the way, times all the way to AI beta minus 1. Yeah, it's a notation, it's a nightmare. And then delta I beta alpha, and I beta plus 1. Beta plus 1 downstairs all the way to AIN. There you go. So beta is not summed over because, well, there's no repeated index here. Beta is not here. This is like 1. Beta is not a sum over. Actually, there might be beta here. Actually, yeah, beta is repeated here. I beta. But the thing is, you get, this is A. Yeah, this is right as A alpha beta, big A beta alpha, where beta is fixed. Okay, so sometimes in expressions you do encounter repeated indices that aren't summed over, in which case these are rarities, in which case you just specify. Okay, yeah, so that's the cofactor expansion. So hang on a second. It says there's two more formulas. It says hence, in the text it says hence you have A alpha j times big A I alpha equals what? Equals the determinant of A times delta ij. Is that right? Remember, alpha is summed over. Here, alpha is summed over. But ij's aren't necessary. Ij's are free. Ij's are free. So I'm not sure how do you get this from that though. Oh, you simply plug in. Or you simply plug in. There you go. The proof is trivial. Here, A determinant times delta ij. Use the formula. So that's A alpha beta, big A beta alpha. Beta is not summed over. And then times delta ij. Is that right? Oh, actually, no. No. No, that's not right. That's not right. So, this formula is claimed but not proven in text. It should be rather immediate, but guys, can you help me out here? So it says A alpha j times big A I alpha is the determinant times the Kronecker delta. So far we have the definition of the cofactor. B is not sum, beta is not sum. So okay, so here AI alpha. AI alpha is fixing. Okay, think about think about one. Let's say A is one. Let's say A is one. Let's look at a. I think it suffices to prove A is one, and the rest of the indices, it just makes your head spin, but it does nothing. So let's verify A alpha A alpha j, okay, A alpha j, and then A1 alpha. Let's do that. A alpha j times A1 alpha. Okay, so this should be A alpha j. A1 alpha is epsilon alpha I2 all the way to IN. AI2 2 all the way to AINN. Says normal thinking, if I equal j, you get the equation above. If I not equal j, should become determined with two equal columns. Right here, Vernon is saying if I and j are the same, you just get the determinant exactly because of this formula. If they're not the same, what happens, right? Yeah, I'm trying to figure out what exactly happens when you have, say, it's like here, so in the formula above, this is A1, A11. and this is minus A12, and this is A13. Right? So if the lower index of little a and the upper index of big A are the same, like here, you just get the regular determinant. Say if you change the lower index for little a to be 2, what do you get? You should get 0 here. But that's what we're trying to prove. For some reason, it is not proved in the text, but to me it's not completely obvious why that should be the case. Okay, so let's see. Can we somehow cook up a Kronecker delta? No, it won't. But why does it vanish though? So I'm trying to figure out how come the Kronecker delta pops up? Yeah, of course, you just need suffices to check the case when I and j are not the same. When I and j are not the same, what happens? So yeah, the idea is, let's say j is not 1, right? If j is not 1, then what happens? When j is not 1, then you have repeated index. Indeed, indeed. Vernon is completely correct. So here, if j is not equal to 1, then this product of all the a's will have repeated lower index, so it's 0. So Vernon is 100% completely right. You have the same 2 columns. So yeah, when j is not 1, then you just get repeated columns. So j is equal to one of the indices, lower indices, and that means the determinant has 2 identical columns. You replaced one column by one of the other columns. This is 0 since j equals 1, 2, or n. This is determinant with repeated columns. With 2 repeated columns. So there's that. Okay. And also, analogously, you have I alpha, big A, big A. Yeah, I remember when I first self-studied tensor analysis, the determinant part was my first pain point. I mean, it's not difficult, it's just freaking annoying as heck. Perhaps that's why I liked Sheldon Axler's linear algebra done right. He hated determinants too. Okay, so yeah, there you go. Same business. Okay, so that's the cofactor expansion that we expressed using the index notation. Yeah, it is a little tedious, right? That's the main thing, right? You just need to grind through it. There's not much deep new math you just learned. In fact, we learned nothing new today. Wow, what a painful comment. Now it's a matter of practicing the index notation. That's not nothing. Because later on, when the actual geometry happens, and then you have to worry about the index notation at the same time, it's going to be a pain, right? So it's better to practice the language first. It's like when you study computer science, you first need to learn the programming language, and then algorithm and data structure. Right? Determinants themselves are beautiful, absolutely beautiful, right? It's just the language that obscures it, right? It's a beautiful chapter in multilinear algebra. It's absolutely beautiful, right? You have, well, once you, I guess, the determinant is usually attracts a lot of hatred at the beginning phase, but then you understand, oh, there's this beautiful characterization of the determinant, and you start to appreciate more and more, and then you see the connection with other areas of math. It absolutely becomes beautiful. Right? It's not arbitrary at all, right? It's the sign volume and all the other things. But it's just the language, finding the right language to express that idea is not always straightforward. Okay, and I was saying that right now we're just practicing the language of index notation, and determinant has to be a proving ground. Happens to be a proving ground because it involves a lot of indices and summations and whatnot. So it's a perfect candidate to practice. There's no new math result being encountered here. Okay, and that's totally okay. Just like in computer science, you learn the programming language first and then do data structure and algorithm, because you don't want to handle all the different categories of difficulties all at once. Okay. So the next example, you have linear equations, also hugely important in linear algebra. In equation, so yi upper index, okay, equals ai alpha x alpha x alpha. So the alpha and I both runs from 1 to n. Okay, so this is a system of linear equations. So now I think what we're trying to do is to derive the Cramer's rule. I think the index notation is supposed to replace actual thinking. In a sense, right? In a sense, notations are meant to facilitate thinking, so that certain part of it becomes autopilot. Let's think about dy over dx. You don't even need to think about the chain rule anymore. No? Right? So it's a nice notation, do that for you. But you pay the cost of learning that notation up front. Okay, so there's that. You have the linear equation, and then let's multiply that by the cofactor. Multiply cofactor, we wanted to do something about this I. So we want to collapse this I. So how do we do that? Let's multiply a cofactor a beta I, a beta IYI, a beta IYI, and that's you can that's just a I alpha, a beta I, x alpha. Hang on. Let's just see if this still makes sense, all right? In the first equation, I is the free index. I is the free, alpha is the dummy index. In the second, I gets contracted, and now beta is the free index, and alpha remains contracted. Okay, so there's that. So that's the multiplication of cofactor. So that now you have a sum over I now. But what is this? Let's use the formula. This is, by the way, this formula are called this is 477, by the way. This formula is called 477, and this is 477A. Okay, so you see, you can use for which one is summed over. What's important is 477. These two indices are summed over, whereas in 477A, these two are summed over. So here we have the situation where these two are summed over, so you use 4777. Looks like the diagonal. So you have the determinant of A times the Kronecker delta. Kronecker delta, that will be beta alpha. Okay, just to highlight what we did here, we used 477 in this portion of the derivation. And then x alpha. And then what happened? Of course, you do the contraction on alpha. And that just gives you x beta. So A determinant equals A determinant times x beta. And because A determinant is just a scalar, you can isolate x beta. So x beta is the cofactor A beta I yi over determinant of A. That's the Cramer's rule. So what this is saying is yi times and sum over, that's the cofactor of ai beta, little I beta. That's the definition of big A in the determinant. Right. The summation is implied here. And then divided by a determinant. So that's the Cramer's rule. Okay. So that's pretty cool, right? The Cramer's rule is just a few steps if you use the index notation. Okay. And now we move on to a crucial object in tensor analysis. That's the Jacobian. In fact, in what follows, Jacobians plays a role in defining tensors, in fact. So this is, I guess, perhaps the most important example we've been seeing so far. So that's the next example. It's going to be the most important. Example 7. Example 8, Jacobian in calculus. And by the way, the Jacobian conjecture was proved by some AI, I forgot the name, it was disproved actually for case where n greater or equal to 3. Okay. So yeah, the future of mathematical research is just verifying AI output. Example 8, yi is a function of n variables. So think of this as a coordinate transformation. All right, so that's so we're talking about Jacobian here. Jacobian, of course, is the determinant. Right? So the prompting is also non-trivial. Yeah, you need good prompting. That's also true. Yeah. So the future of mathematical research is a matter of designing prompting and verify the output. Okay. Okay. So, indeed. So it's like the future of mathematical research is literally leaving exercise. Is literally leaving exercise to the AI. Right? Isn't that an appropriate description? Okay. We know that from calculus, if the determinant dy over dij d over dxj is non-zero at point the four-color theorem is still different from AI-assisted proof, right? Four-color theorem is something that the algorithm to verify the four-color theorem is hard-coded. It's not generated. So from calculus, the determinant at zero and the partial derivative continuous implies invertibility, local invertibility. This implies local invertibility. That's basically the inverse function theorem. That proof is highly non-trivial. But all the AI hype around this is how the market behaves, right? So I think mathematicians will survive. Okay, I think I'm optimistic about it. Mathematician as a profession will survive. Local invertibility means xi can be written as a function of all the y coordinates in some neighborhood, in the neighborhood of P, that local invertibility. Right? The Jacobian conjecture, which was disproven, was about global invertibility. Right? It says if the Jacobian is a non-zero constant everywhere, does that guarantee global invertibility? Turns out it doesn't either. Right. All right. So here, so we have this identity, basically the inverse matrix relation. Identity. We know the Jacobian and the inverse Jacobian, of course, they're inverses, right? It's completely trivial. So you have delta ij, the identity matrix element equals dy I over dij dij. I think this will affect the perception. That's the thing. Buckingham is absolutely right. Mathematics is a highly creative field, right? Exactly. Being a mathematician, prompting is not a mathematician. It's like generating an image. It doesn't make you an artist. Exactly, right? But it's gonna. It's like AI is gonna change how artists work. The same way it will change how mathematicians work. And exactly how is still a bit unclear, right? And when during time of change, people are have anxiety, and that's completely normal. Right? This is sort of the liminal space we live in. Something is about to happen, and there's this sense of dread and hope, and it's completely normal. So this is the identity we derived earlier. Right? It's a trivial identity. dyi over dyj is the Kronecker delta ij, and you can write this as a chain rule. So dyi over dx alpha, and then dx alpha over dyj. Right? So that's the chain rule. So in the second, you use the chain rule. The first is the identity we shown earlier. And now we can use the determinant property. Right? Determinant property, which we proved earlier, the multiplicative property of determinant. So taking determinant both sides, is 1 equals the determinant of dy over dx determinant times dx over dy determinant. Right. So the Jacobian is defined, the Jacobian determinant is called, sometimes it's simply called the Jacobian, because it's a little bit annoying because you have the Jacobian determinant and the Jacobian matrix. It's usually clear from the context, but you still have to distinguish the two. Right? What I dread is AI judge putting me in jail because efficiency more doing things properly. Yes. Yeah, this is, I mean, I'm not sure about putting in jail, but you know, this is efficiency is valued above all. This is a great disease of neoliberalism. Like efficient, it pretends to be value neutral, but it implicitly places efficiency above everything else, which is really pathological. Anyway, enough rant. Let's define determinant. Define Jacobian as the determinant. Anyway, so this is the same as the is the same as what we usually write in calculus. There are different ways to write this. There's just different notations. Okay, Jacobian seems to suffer from a lack of universal notation. I know I sound preachy, huh? Y1 all the way to yn. We don't usually bring up other math creators on this channel, but maybe you guys know there's a channel called City Tutoring. Speaking of preachy, it's fair to say that guy is preachy, huh? But I have no intention to start wars, okay? Just he can do his own thing. It's totally justified. But I'm just try to stay away from the drama. But you know, some efficiency above all else is indeed a great disease because there's no guarantee that publishing means understanding and actual progress. Right? All of analysis lacks universal notation. Perhaps epsilon delta is still kind of universal. Huh? This is one way to write this. Big D, yes, big D. Big D, I use big D for you see that a lot in advanced calculus like such as the one by Spivak. Big D, that's a good one. Big D is a little, I don't know about little d, but big D is something I use often myself as well. Okay. And I use big D to represent the matrix. Okay, so you know what? Why don't we just use big D? Here, big D of, just use J or J. Yes, that's also okay. Actually, you know what? Sorry, because here big D is not really appropriate because big D is the matrix. Here we can just, we use J. Actually, that's the one the textbook uses. Harry last used this big J. Which is fine. Someday this will be standardized. I'm pretty sure about it. All right, so there's that. We have this is the Jacobian, and next example next example here, it says what? The next example looks rather sophisticated, which is a good thing. Let's try to elucidate that. Example 9. What I like this book is there's a lot of examples. It says if the elements of the determinant are functions, we leave it to the student to prove. Okay, challenge accepted. It says if the elements of the determinant absolute value, a determinant of A, so to say. Here A is an array, okay, Aij. Our functions of variables. Our functions of variables x1 all the way to xn. Then what happened? Then it is left as an exercise that the determinant of A taking partial derivative with respect to x mu is the cofactor A alpha beta times d a alpha dA beta over alpha over partial x mu. Interesting. Essentially a gradient of vector field. Yes, gradient of vector field instead of a scalar. You mean the gradient of a yeah. So here we're trying to prove this identity here. Proof. This is left as exercise in the textbook. Well, we're probably going to use the cofactor expansion. So A determinant, well, we showed that earlier. So A determinant had these representation. So A determinant, you can write it as A alpha beta big A alpha big A beta alpha. Here we can write it as big, say, so here there is a big A alpha beta, so let's pair that with a little a, beta on top, alpha at the bottom. Okay? Remember, everything now depends on x, so you cannot just assume constant. So differentiation would require a product rule. But how come there's only one term? How come there's only one term? Well, let's think about that. X mu equals, by the product rule, this should be A alpha beta dA beta over alpha over dx mu, and then plus A beta alpha and then d over dx mu big A alpha beta. Yeah, eventually we'll get to that. I think in the information geometry stream, this is one of the very first idea. Taking partial derivatives gives you tangent vectors of a manifold. So, but the thing is, how somehow this vanishes? What the hell? It says if the elements of the determinant are functions of the variable x1 all the way to xn, we have the following. So a determinant over dx mu is a alpha over beta, partial derivative of a beta over alpha over dx mu. What's going on? So you use a cofactor expansion. Okay, so when we're stuck, let's try a special examples. Let's try a special example. Say you have a. Okay, I don't know how to proceed. So you have a11. What does the example supposed to look like, right? So let's say you have a11, which is a function of x1, x2, just 2 by 2. This should suffice to illustrate the result. Okay, a21, and finally a22, x1, x2. So this is a determinant. Of course, you expand it. And now I'm just going to suppress the argument. Okay, a11, a22 minus a12, a21. So differentiate the determinant relative to, with respect to x1. What do we get? Well, the first term is use the product rule. The first term is use the product rule, so you get the dA11 over dx1 a22 plus a11 dA22 over dx1 minus a d a12 over dx1 a21 minus a12 dA21 over dx1. Right? So there's that. So judging by the final result here, there should be two summation going on. And indeed, there is, right? There is two summation going on. So, yeah. The cofactors. But the problem is, why isn't there a derivative with respect to the cofactor? How come this just vanishes? Or did I misinterpret this result? Actually, in this cofactor expansion, beta is fixed. Remember, here, in the definition of cofactor expansion, here, beta is fixed. Perhaps we should use 4777. Okay, let's write that down, and perhaps we can do something about that. Notice that here, the equation I use, this only does one summation. In this format, in this definition of a cofactor expansion, you fix beta or you fix alpha. So there's this might not be correct. Okay, chances are the approach we took is not gonna give us the answer. So um, I'm just saying, can we say I'm just entertaining the idea of replacing delta aj as a derivative. Hmm. Cofactor seems annoying at first, but they define explicit solution. Yeah. So I know like here we wanted to show that the derivative of the determinant. Why is use? Hmm. Here in the formula there should be a double summation going on, but in this cofactor expansion there's only one. There's only one summation index. Beta is considered fixed, so I'm a little bit confused here. Cofactor. And we hmm. Guys, I think I'm going to cheat and I use AI. Okay, sorry about that. But because I'm genuinely stuck here, this is I don't know which formula I should use. Perhaps you know what? Let's go over before I uh, throw in the towel and cheat. Let's take a look at what happened earlier. So here we introduced cofactor, and now do we have perhaps something we can do to give it to a alpha beta? There's perhaps there's something obvious that we're missing, right? So far we didn't use a lot of results with cofactor. Hmm. Let's say, if I mean this is we can say you need to sum over all the columns of cofactor. Is that usual? Yeah, it turns out, I mean, the 2 by 2 case, you do need the derivative of the cofactors. You do need the derivative. So why does the second term just vanish, huh? Hmm. So if here in the definition of the cofactor beta is fixed. So this means here beta is fixed as well. If the determinant isn't exactly 0, it must be related to indexing. So it's a matter of interpretation. It's a matter of interpretation. We used the cofactor definition, even though it looks like a double summation. beta is considered fixed. It was explicitly mentioned before that beta is not summed over. Look here. See, beta is not summed over. It is explicitly stated that way. Hold on. Yeah. Here, beta is fixed, not summed over. Now, if we use that, then we have to keep things consistent. So beta is just an arbitrary index, like 1, which is not what this result is about, right? In this result, you need to sum over both indices. So can we maybe use a chain rule thing? Can we do that? So why don't we try that? Say, let's try again, okay? So dA over d x mu. This is dA determined over dx nu times dx nu over dx mu. So this way we can cook up a Kronecker delta. So this becomes d over dA. So this is the determinant of a over d x nu. That's a Kronecker delta u nu mu. All right. Of course, nothing is done here. Nothing is done here. These two are the same. But let's consider something like this. So let's consider what's the a determinant delta nu mu. Right? We have something like this, right, before. Here you go. So this way, I was trying to create a summation. There you go. Summation over the cofactor. Okay, so you have this result. So this is 4777, by the way. And that's just A. Okay, so based on, just consider the formula, A absolute value, A determinant times delta nu mu. Okay, big A, nu on top, say alpha at the bottom, A alpha on top, and mu here. Mu here, okay? So there's that, and then let's differentiate that. Here, nu and mu are free. Can we d over d mu? Can we d over dx mu? D over dx mu. On the left, you get x nu. Okay, we need x nu here. D over dx nu. Let's try that. So on the left hand side, you get a product rule, which is dA alpha mu over dx nu, A nu alpha plus A alpha mu, dA nu alpha over dx nu. That's a product rule on the left hand side. On the product rule on the right hand side is dA determinant over dx nu, dx nu times the delta nu mu. This is what we want, and the last term dA, no, not dA, but simply just A determinant times hold on a second, delta nu mu over dx nu. It does absolutely freaking nothing, no? It does absolutely freaking nothing because the partial derivative of delta is always zero. It's a constant. It's always zero. So this here, what do we get? We run into the same problem. We run into the same problem. You have two terms. How come? My goodness. There should be a double sum here. But here we have no. Yeah, a the double sum, but in the wrong location though. In the wrong location. Here mu is supposed to be summed over. No, mu is not even summed over. Mu is not even summed over. It's the lower thing gets summed over. Huh. It's perhaps we're forgetting a restriction of the equation. I'm asking because I would expect 2 by 2 case to satisfy the Cauchy. No. There's no Cauchy-Riemann going on. Cauchy-Riemann, that's a special requirement for analytic function. Okay. No. There's no Cauchy-Riemann going on. So Cauchy-Riemann is something different entirely. There's no extra restriction, as I'm saying. This is purely an artifact of differentiation and the definition of determinant. Cauchy-Riemann is an expression of conformal maps. This is just an arbitrary, this is a determinant, for Christ's sake. Oh no. Because the 2 by 2 case is correct. I'm just struggling to see the Okay, perhaps we should pursue this a bit further, okay? What are the cofactors? What are the cofactors? Here, if we use the right-hand side, what's the right-hand side here? Okay, remove everything here. This is pure garbage. Doesn't work. Doesn't work. So this is also garbage because, I mean, let's just leave it here. This is as close as we can get, right? We used the definition, but it didn't work. But what's on the right-hand side? Right, we never tried the right-hand side. So the right-hand side corresponding to this one should be A, where we picked. Do we pick anything? No, we didn't pick. Well, we picked mu equals 1. So on the right-hand side, we should check A alpha beta d of A beta alpha, yeah, and then over dx1. So we need that. So expand that fully. So first of all, let's just keep all the derivatives at the same place. So you get dA11 over dx1, and then dA12 over dx1. Actually, you know what? dA22 here. Let's use 22 over dx1, dA12 over dx1, and dA21 over dx1. Okay, and it should be multiplied by A. Okay, so beta is downstairs in big A, alpha is upstairs, so it's still A11 plus A, you swap, okay, swap 2 down here. Okay, 2, 2. It does not matter. And then plus big A, 2, 1. And then finally plus big A, 1, 2. Okay, so this is what we should have. And now let's take a look at what is A11. What is A11? So look at the matrix. A11 is what you erase, what you get after erasing the column and row consisting of A11, which is A22. A11 is indeed A22. So we're good. So the first term is good. So we have 4 terms in total. Should be a double summation. So A11 is indeed A22. What is A22? A22 is A11. So that's good as well. What is A21? A21, after you erase a little A21, you get A12, but it needs to pick up a minus sign because 2 plus 1 is even. 2 plus 1 is odd, so that's a minus A12. A21. A21. Hold on a second. Something's messed up, huh? A12, A A A12, if you remove that, okay, but that's the linear algebra definition. What is A21 in the definition here? In the definition we have here. In the definition we have here, A21 should be A21. A21 is the Levi-Civita symbol. One, two. Actually, what is A21? I can't. You see, this is I'm not still familiar with the language yet. What is A21? If we use this expansion, then Aij for n equals 2, if let's say that should be a epsilon ij ai1 aj2, so above 777, where above 7, this part, yeah, here, yeah, I know, I'm just trying to write down age hold on, what do I want A21. So A1 alpha is obtained by taking out the first one. So I need to take out AJ2. So AJ2 epsilon ij AJ1, like this. And you simply call that, A alpha 2 times A2 alpha. A2 alpha. So A2 alpha, where A2 alpha is so the free index have here, which one gets contracted with J? Well, J gets contracted with J, so that's epsilon I alpha AI1. Okay, and now specialize alpha to 1. Big A to 1 is epsilon I1. Epsilon I1 and AI1. So only there's only one non-zero term, that is epsilon 2 1, epsilon 2 1, A 2 1. So yeah, it's just A 2 1, and it's minus A 2 1. So big A 2 1 is minus A 2 1 indeed. So yeah, I was able to follow the definition. Thank goodness for that. So this is verified. And finally, A22. Is that A22? Sorry. A12. The cofactor A12. A12 is the hang on. A12. Let me recall the definition. Cofactor A12 is epsilon 1 I need to do the same thing over. Aij. Determinant is epsilon ij. A12 is obtained by factoring out A1i. No? Like this. Basically, I'm rederiving the cofactor. A1 alpha is epsilon 1 alpha, A alpha 2. That's A1 alpha. So A12 is epsilon 1 2. A22. That's nonsense. God damn. Okay. So what did we make a mistake? Where did I make a mistake? So here in the 2 by 2 matrix, A12, this still bothers me a lot here. Even though formally I got the right answer, this still bothers the heck out of me. Because somehow the cofactor of A12 is minus A12? This still bothers me. Like, no wonder I can't even derive this, because I don't understand what is A alpha beta. What on earth is this definition? Hold on. Let's look at this cofactor here. This cofactor here. What's okay? I'll give the original text in the book. here. It says, this is what it says, okay? So it says, in general, this is a text. It says, in general, here, okay, I don't want to place these two side by side. This is what I copied down, okay? The determinant of Aij is A alpha beta times this symbol here, Levi-Civita symbol, times AI11. Okay, see, why is there a delta here? Why on earth is there a delta? Why can't you just take out the factor? Big A alpha beta is the thing inside. Yeah, I think I was suspicious about this delta. Why is there a delta? Remember, when we take out AI1, we didn't do any funny business with delta. You see, why is this thing needed? Is there a summation going on here? Because epsilon in the front does not have I beta removed. No, epsilon is intact, right? Remember here, when we put the factor AI1 up front, we didn't do anything about epsilon. Huh. What is going on here? Is there implied summation somewhere? There shouldn't be, right? Because alpha here is free, and so is I beta. Yeah, alpha A1 alpha has I replaced by alpha, I1 replaced by alpha. Yeah, exactly. Here you see, I1 is replaced by alpha. It's just change in the free index. Because in this part, everything other than I1 is summed over. So I1 just get renamed to alpha, nothing going on here. So what happened here is that in the definition of A beta alpha, which one is free and which one is summed over? Beta is supposed to be fixed. See, beta not summed. So alpha is summed over. In the final expression, alpha is summed over. And of course, this means A beta alpha has two free index. Delta's effect is in the general index replacement. So let's imagine if I beta does not equal I beta does not equal I, then okay, so hold on a second. Let me continue this. So A, according to this definition, okay, according to this definition, then A beta alpha should be so simply by taking out the factor A alpha beta. So A alpha beta. So here, let's think about what are the free index here. A alpha beta, let's just take this at face value. This is epsilon because I'm still suspicious of this. I don't get this. Epsilon I1 I2. So nothing is done here. Nothing is done to epsilon. And then AI1, 1, all the way to AI beta 1, beta minus 1, beta minus 1. Okay, I hand waved over this, and now I just copy it down without thinking much about it. I said, oh, I'll just take out the factor, and now it's biting me in the butt. So what is this? What on earth is this? So because there's nothing done to the first epsilon, so I beta appears somewhere. I beta appears somewhere, so there's a summation. So there's a summation. Remember, let's take a look at what is being summed over here. Is there, first of all, is there a missing index that is not summed over? And what is, okay, here you have an alpha in a delta. Which one, so alpha is being taken out. I am just completely frozen right now. I have no way to go to proceed. It's painful. This is extremely painful. So remember here in A1, why can't I just go from A1 alpha to big A beta alpha? Renault says delta replace the subscript. Delta replace, so because you're summing over I beta, right? Are you summing over all the indices? I think so. So everything is summed over. So when you sum over a delta term, then what happened? Then only the then in the summation, the only non-zeros are the ones in which I beta equals alpha. That's what remains. So in fact, all the i's get summed over. Here, all the i's get summed over. All the i's get summed over, and I beta must equal alpha. So this is, in fact, let's just write it like so. So this is the same as, perhaps this is where we're missing here. Because of this delta business, you have epsilon I1, I2, all the way to I beta minus 1, I beta plus 1. Actually, not I beta plus 1, just I beta minus 1, alpha, I beta plus 1. Because it should go from I1, I2 all the way to IN, right? And at some certain point, I beta gets replaced by alpha. Is that what happened? And then IN all the way to IN. There you go. And then you can just write, okay, AI1, 1. Okay, all the way to AI beta minus 1. Beta minus 1. And then delta is 1 now. So don't need to write that. AI beta plus 1 over beta plus 1. all the way to AINN. Yeah, so this is what happened when you take out when you extract the factor, right? The factor AI beta. Yeah, AI beta. Hold on. Well, let's just rewrite it from scratch. AIJ, by definition, is AI epsilon I1, I2, all the way to IN, AI1, 1, all the way to AINN, right? And you just pick the I beta, actually the beta index, the beta term, you pick out the beta term. So by picking out the beta term, you should get AI beta at the bottom, epsilon I1, I2, all the way to IN, AI1, 1, all the way to AI beta minus 1, beta minus 1, and then skip the beta term, get I beta plus 1, beta plus 1, all the way to AI m plus 1 over m plus 1. Okay, so that's the factorization. I mean, not factor, yeah, just the factorization. Yeah, that's correct. So now you see, oh, sorry, I messed up something. I did not do anything with symbol here. Did I? Did I do anything about the symbol? And actually, should I do anything about the symbol? There's nothing needs to be done, right? Here, nothing needs to be done. Just like in the factoring out the first term. Nothing needs to be done. This is just that. Okay, so after that, I'm going to rename I beta to alpha. Rename I beta to alpha. This way you get, yeah, Vernon is trying extremely hard to help me out. Thank you so much. Because thank you so much. I'm just slow. Sorry about that. So if I switch I beta to alpha, that means in the epsilon, I need to change I beta to alpha. So I1, I2. I better put this instead of what I just wrote in the notes because that was useless to me. Okay. Perfectly obvious for the author, but not to me. So what you end up doing is we want to swap I beta to alpha. So this was what happened in the epsilon. Okay. And the rest remains the same. Because here there's no I beta. I beta has been taken out. So what happened? So here nothing happened, right? So this is just unchanged here. Okay. And now we're going to write this as, encode this as a delta. Yeah, so delta does exactly what Vernon said. So use the fact that here is a general property. You can say delta ij a what? aj ai. It just replaces the index. Delta does this index replacement thing, yeah, as was mentioned by Vernon. So you see here we just replace alpha by we replace I beta by here we replace I beta by alpha. You can just multiply that by a delta to represent that. Okay, so finally this is all cleared up. This is finally all cleared up. So thank goodness for that. So that's, yeah, basically here. So this way we derived the A beta alpha expression. Okay, thank you so much, Vernon. I apologize for such an obvious error. Okay, because hopefully this will help us out to prove the formula, because this delta can be useful, huh? Help with the contraction and whatnot. So here in this note, in this expression, both alpha and beta are free. Oh, there's a mistake. There's no n plus 1. Oops. Okay, made a mistake here. Oh no. Yeah, the definition is quite hidden. So I think I need extra space. So basically, I think, yeah, I'll get rid of this part. You know what? I'll do the reorganization of note later, but here, I think there's also some mistake here. This should be n plus 1. It's just n, okay? A-I-N, n. And this is a beta alpha. This is A beta alpha. So A beta alpha is now known. And let's come back to the problem. Okay. A alpha beta is times this partial derivative. How do we cook that up? Determinant of A, we face the same problem. So now the definition of the cofactor is cleared up, but we still face the same problem. How do we cook up a double summation? If we just differentiate this, you still get a single summation. So that's why I was thinking, oh, perhaps you could or erase that now. But perhaps I was thinking you could get a pair that with a chain rule and see and do a summation there. Okay, I think it's because we still have like half an hour left. So I want to, because I want to take some rest tonight. I still have measure theory. Okay, so I just wanted to say, because we give a fair attempt. Okay, so let A, let's it looked like it should be it looks like it should be a double summation. You see here in the 2 by 2 case there are 4 terms. It should be a double summation. So consider a determinant A whose entries whose elements are functions of x1 all the way to xn. Find a formula in summation convention for, just say, I just want to give the form for the partial derivative. Google says D. Summation notation. Wow, it actually suggests the word notation. I use summation convention. It suggests the word notation. Wow, Grammarly, well done. I see. You're differentiating with respect to the entry, right? Yeah, you're differentiating with respect to the entry. Perhaps that's a good starting point. You know what? Or delay that. Let's think about just how do you differentiate with respect to the entry? Say dA determinant over d an arbitrary element. Say arbitrary element a beta alpha. Well, A is what? A determinant is, say, why don't we just write it as, as an arbitrary cofactor expansion. You pick, just like when you evaluate the determinant, you don't you don't keep messing, you don't change the choice of expansion, right? So that's I'm trying to get to. So why don't we just write it as A, okay? A, I can't use alpha anymore because it's a free. So let's just say AI1 times big A, 1I. Can we do that? And let's say D over D, A beta over alpha of this thing. AI1, big A, 1I. So you get D AI1 over dA beta alpha A1I plus AI1 d A big A 1I over dA beta alpha. Does it make sense? Okay, so the first one we can use the Kronecker delta thing. So you need delta, does that mean delta I beta and delta alpha 1? The thing is, this can only be 1 if beta equals I and alpha, beta equals I and alpha equals 1, right? AI1, and I have no idea what this is. One thing is for sure, this equals 0 if, actually I don't know. I still don't know. Like, yeah, I'm trying to prove the identity given by Vernon, said in the chat. So just differentiate with respect to the entry. Yeah, that'll be in the step in the right direction. So what is the determinant? What is the partial derivative of a determinant with respect to its entries? With respect to one of its elements. Okay, suppose aij is an n by n determinant, and then you take the derivative with respect to aij. It's just the cofactor. It's supposed to be just the cofactor. It's just the cofactor. It kind of makes sense, no? It kind of makes sense simply because of this definition. Actually, let me erase all of this, because I'm not even sure this is right. I may have to do a little bit more concrete examples later, but basically, this is the reason. It's like if you take the partial derivative with respect to a alpha 1, yeah, that's the only variable used in the cofactor expansion. Right. So here immediately you can say d determinant over d a alpha 1, this is just a cofactor. No summation. Right? And of course this 1 can be replaced by beta. So let me just actually erase this and put it right next to, oh, I'm supposed to, okay. Yeah, I will do this exercise myself and leave space for that. But basically, here we should have dA determinant over dA alpha beta equals big A beta alpha. You should have that. Yeah. That's the only variable that is used in a cofactor expansion. I know, right? So, okay. Hold on. Okay, so if we can take that, let's come back to the problem. So use the chain rule dA over dAij, and then dAij, not ij, but not ij, alpha beta. Okay, I'll try to respect the index notation. A alpha beta, and then do A alpha beta. That's it. That's literally it. Just one step. That's just the chain rule. My goodness. So yeah, the proof is just literally one line. Okay. Okay, I was silly. I wasted like half an hour, or if not more. Yeah, so there's no trick to it. The only thing matters is the determinant taking positive with respect to the entry, with respect to the element. And after that, everything is, there's no need to keep any of these. Okay. Okay. Oh my God. All right. Lesson learned. What can I say? Yeah. Since A, the determinant is A beta alpha times big A alpha beta, beta not sum, or doesn't matter, does it? Which one is sum? I think in the original definition, here, in the original, which one is not sum? In big A, which big A here. Oh, I deleted it. That's not good. So basically, A determinant is A alpha beta. Hold on a second. A alpha beta times big A beta alpha, where beta is not sum. Just do a double sum with all beta. No, it's not a double sum. This is not a double sum. Just like here. This is just a single sum. The cofactor expansion is a single sum. You sum over a row or a column, not sum over all the entries. That's redundant. Right? An n by n matrix taking a cofactor expansion has n terms. Okay. Yeah. What did it's like here? What did AI say? Prove this immediately follows the Laplace expansion, because CIK in the cofactor contains no AIK anymore. So it's just a linear function. Yeah. Not using cofactor expansion here, but the chain rule over. Yeah, when you do the chain rule, yes, you need to do a double sum. Yes, exactly. You're completely right. But because of the summation notation, there's no need to write the sum, explicit sum. Okay, so alpha beta, hang on, which one is not summed over? Alpha is not sum. Okay, and then dA over d dA determinant over dA alpha beta, that's just A alpha beta. Okay, alpha beta. Yes. It is confusing as fuck. Sorry. So basically that's just that's there all there is to it. Because the cofactor is independent of A beta alpha is independent. That's it. Of A alpha, A beta alpha. Okay. So then you use chain rule. So just dA determinant over dx mu, and then equals dA determinant over dA beta alpha. You see, summation convention is used at this step, not here. This is summation. And boom, you're done. It's just A alpha beta dA beta alpha over dx mu. So QED. Okay. Okay, so that was embarrassing, to say the least. But I think it's a good exercise. Yeah. So let me just fix this real quick in case I forget. Can I erase this now? Thank you. Because sometimes OneNote, the mouse location is messed up. You see, it's still messed up. I can't click this thing. Okay. Okay, perhaps this is too complicated. This is such a no. Okay, okay. It's stuck. The software is stuck because I don't know what. I might need to close a few things. Okay. Let me close MS Word. Okay, let me close the ChatGPT. Okay, perhaps this will make the computer a little bit. Yeah, okay, so now computer can breathe. Thank you very much. So basically, yeah, thank you very much, Vernon, again, for your patience. I am very slow, but it's okay. We will get better. I will get better. You know, by saying we, I always mean myself. But because when you write math, you always say, we assume, let us consider. You know, my mistake are my own mistake, okay? Not the viewer's mistake. It's just, it's habit. When you write math, you never use first person pronoun, right? So you always first person singular pronoun. You always use first person plural pronoun. And usually say, oh, we figured it out. Usually it's other people figure it out. It's other people help me in chat figure it out, not I figure it out. If I have no help whatsoever, I will just get stuck with this definition. Okay. Hopefully we can move on now. Okay. Squeeze a little bit downstairs so the derivation can have space. A little bit upstairs. Yeah, so this is the cofactor expansion, derivation, and definition. The general definition of A alpha beta. And a trivial consequence of that, which is the key to the exercise. Okay. So this is the definition for the general A beta alpha, where delta plays the role of index replacement, and this is the definition. Yeah, there's no mystery because once you consider the derivative with respect to matrix element, and then apply the chain rule, there's no need to do the product rule, right? So there you go. It's a matter of chain rule. Okay, so that's done. Okay, so this is the example 9, but there's some continuation of that example. There's a special case, as the text says. There's a special case. We'll finish at 4, so 15 minutes. We'll call it a day. So not a day, but there's evening stream on measure theory. Okay. So special case is as follows. So suppose you have, yeah, it's a chain rule. See, we don't need a product rule. If you use the product rule let's say if you use the product rule here, if you use the product rule here to do this step, when you differentiate with respect to a alpha beta, the partial derivative of the cofactor with respect to a beta alpha is 0. So there's no need to do product rule. Okay, so as a special case, it says suppose Aij is the Jacobian. Is a Jacobian matrix, Aij, okay, is dyi over dxj. So that's the Jacobian, where yi is a function of n variables, x1 all the way to xn. Okay, yeah, all right, so there you go. We have this Aij. And now it says, now consider the identity delta ij as dyi over dyj, of course, and then use the chain rule dyi over dx alpha. We already derived that earlier, but just to clearly see that again, dyj. So that's the chain rule. And let's consider j to be fixed for the moment. Okay, fix j for the moment. Okay, cool. Okay. Fix j for the moment. It's not a free variable anymore. Fix j for the moment. And let big Y I don't know where this is going, but I'm just repeating the text. Big Y is delta ij. So imagine delta ij is the elements of identity matrix. And now you're fixing j, so you're fixing the column. So as I varies, it runs down the column. So that's yi, a column of the identity matrix. So here okay. Look at this expression here. Look at the expression here. So let's write delta ij to be y, so that yi is here we have the first term. You see the first term dyi over dx alpha. That's a. That's just ai alpha. That's just ai alpha, and then times. Oh, actually, you know what? Let's give the second term another name as well. Second term dx alpha over dyj. Hi. Okay, sorry to hear that. Yeah, it hurts, I know. Yeah, my condolences. Remember, j is fixed, so we can write x alpha as dx alpha over dyj. Okay. Sometimes this is what happens, and perhaps it's better to end a relationship early rather than later. Okay. Yeah, I mean that's on her. That's on her. Then like, don't worry about it. I mean, I know it's very hard right now, but I guarantee you this is not the end of the world. Okay. Okay? It hurts. It's normal. It's normal. I don't know what else to say, but you can get through this. Okay. So I was saying that this differentiation formula, basically the chain rule, delta ij is now replaced by y. It's just pure notation. And then times a I alpha, that's the Jacobian of y with respect to x, and then times x alpha. So there's nothing else but just notation. Okay, and if you have, yeah, don't worry, it's life. You'll get through this. So if the determinant of a is dyi over dxj is non-zero, then we know that you can use the Cramer's rule. If this is non-zero, by the Cramer's rule, which we derived earlier, so you have x beta. Remember, this is a linear system of equation. X beta is y alpha times the cofactor of a alpha beta in the determinant over the a determinant. Okay, this is horrible, but yeah, over the a determinant. So that's the Cramer's rule. Or you can write this in terms of the original partial derivative. What is x beta? It's the same as dx beta over dyj. Okay, and then expand that. So y alpha. Remember, y alpha is. Remember, y alpha here. yi is delta ij. So y alpha is delta alpha j. And then times the same cofactor. So cofactor of a alpha beta. So a alpha beta, actually a alpha beta doesn't need to be changed, but a alpha beta means what? A alpha beta means dy alpha over dx beta in the determinant, in the same determinant. So in the determinant, which is dy over dx determinant. All right, and then divided by the a absolute value, not absolute value, but determinant. Okay, actually, let me just change that to partial derivative as well. Dy dx, the determinant of the Jacobian. It's the same thing, right? You just use the Cramer's rule. So you can actually express. You can express the cofactor. Hang on. And you can do this, first of all, actually do the summation up front. How do you do the summation? Well, if you have a delta, the alpha is a repeated index. Alpha is a repeated, you say, oh, alpha is a repeated index, but it's both upstairs? That's weird. Don't be weird. Don't be weirded out. So the cofactor of dy alpha over dx beta will have alpha in the downstairs. So there's no contradiction there. So basically this just becomes the cofactor of dyj over dx beta in the Jacobian. Dy over dx, absolute value, over the partial derivative dy dx taking determinant. Okay, that's the Jacobian. And so now you have I still actually, you know what? We understood every single step. We understood every single step, but I don't know why. Where we're going here? Where on earth are we going here? It says it's a special case. I don't see why this is a special case. It says it's a special case. Still, anyway, we haven't finished. Perhaps there's something that comes up later. There's a punchline, perhaps, somewhere down the line. But what happens is this. So you have the cofactor of dyj over... Yeah, I remember when I first self-studied, not from this book. Yeah, I forgot which book I even... perhaps a set of notes, like almost 10 years ago. I also had to just slog through the determinant part. There's no deep result, new result that you learn. It's just kind of tedious. Anyway, so here you have the cofactor of dyj over dx beta in the Jacobian determinant equals what? Equals dy over dx, that's the determinant itself, times dx beta over dyj. Okay. So this is what we have so far. And now we can apply this to example 9. Okay. So apply this to example 9. This is perhaps going to be important later. Apply this to determinant 9. The example 9. Now A alpha beta, that's the cofactor, right? Is a cofactor. So A, remember, is the Jacobian determinant. Jacobian determinant taking positive with respect to x mu. Okay, so let me just put everything together. So this is the formula, which we just showed earlier. And the cofactor, A now is the Jacobian determinant. So let's apply that. To example 9. Okay, this is the equation. So we have the partial derivative of the Jacobian. So d of dy dx over dx mu is what? Is the cofactor. So we now have an expression for the cofactor now. Okay, it should be okay, so A alpha beta, big A alpha beta, that's the cofactor of A. Is it alpha beta or beta alpha? Remember here, yeah, A alpha beta is a cofactor of A beta alpha. And A beta alpha, which is equal to here, Aij, is dy beta over dx alpha. Okay, cofactor of this thing in the Jacobian determinant, dy over dx. Okay, and then times d beta alpha, A beta alpha over dx mu. Okay, substitute here. We have the determinant dy over dx, determinant dy over dx times, I'll finish this and I'll call it a day. Okay, so, and then times the dx beta over dyj, and then times dA beta alpha over dx mu. Oh, actually, I forgot to replace alpha beta, a beta alpha, a beta alpha. That's just the. Hold on. Oh, hold on. That's not right. That's not right. I forgot to change the index here. Beta should be on top. The cofactor of dy beta over dx alpha. Here we have j. Okay, j is downstairs, so here you have a beta here, and alpha is on top. dx alpha over dy beta. There you go. And here you have dy beta over dx alpha. Yeah. Yeah, so you can write this as a second derivative. So or you have this 1 over dy over dx determinant, dy over dx determinant over dx mu, which equals dx alpha over dy beta times d square y beta over dx mu dx alpha. It's just a definition of second order derivative. But on the left hand side, we notice something. This is the partial derivative with respect to a log. I use the chain rule, single variable chain rule. This is d over dx mu of log of the determinant. Okay, so this will turn to be useful. Okay, so this result will turn out to be useful. Okay, so we're going to call it a day, and we'll see you guys next time. All right.